Hi, students. This is the second part of the, or continuation of the magnetism lecture. So again, chapter 21 on magnetism. Continued. Okay, so the last time we discussed, or in the previous part of this lecture, we discussed the Lorentz force law, and that is the force that a magnetic that a moving charge feels in the presence of a magnetic field. So again, we talked about this is a fundamental force law of the universe. It is always true. There's no primary reason for it to be true. It is one of the fundamental forces of the universe. So again, the Lorentz force law looks like the following. It says that if a charge Q is moving at a velocity v and it's in a magnetic field, it experiences a magnetic force given by QV cross B. So you take the cross product, which we talked about previously, the cross product of the velocity with the magnetic field, and so the force is gonna be, so the velocity of the magnetic field will be two vectors that would form a plane, and the force will be perpendicular to that plane. And again, perpendicular to a plane could mean there's a twofold ambiguity. So let's say if I have a force vector and a velocity, let's say in the plane of this whiteboard, well, it could either be out of the whiteboard or into the whiteboard. Which is it? That's determined by the right-hand rule. Again, little review there. But the thing about it is, this is a fundamental force law. In fact, we're actually at a point where we've actually derived we've actually shown or have the entire electromagnetic force law. In fact, the actual electromagnetic force law, I told you that electromagnetic theory is based upon 4 equations called the Maxwell equations, which relate time, space, magnetic field, and electric field, and the fundamental force law of the universe. So we saw there's 4 fundamental force laws. We saw one of them in physics 1, that's gravitation. This is the second, a fundamental force law. We'll talk about the other 2 when we get to chapter 31, we talk about nuclear physics. So again, the overall electromagnetic force law, maybe put an EM for electromagnetic. The overall electromagnetic force law is going to be QE plus QV cross B. So again, you can think of it maybe this way. Electromagnetic force law is the electric force we talked about earlier in this class, plus the magnetic force. And so again, if an object has a charge Q and it's in an electric field is present, it will feel an electric force. If a charge is moving in a magnetic field, it feels the magnetic force. So the total electromagnetic force that a charge could feel is a combination of both of these forces. All right, and we saw in the Hall effect in the previous part, the Hall effect showed you a nice, beautiful combination of how the electric and magnetic forces work together. We saw that because there's a magnetic field perpendicular to a conducting strip, that separated the charges. Negative charges went to one side, positive charges went to the other side. But because you had charge separation, you developed an electric field. And eventually it got to a point where, remember in the Hall effect, that the electric field and magnetic field actually, the electric force and magnetic force actually counterbalanced. So at some point, the charges will no longer feel this tendency to be deflected to one side or the other. All right, so anyway, we see this interplay. So now, one of the problems with this particular version, yes, this is the official version of the Lorentz force law, but you're very highly unlikely to be personally in contact with a separate moving charge and moving in a magnetic field. You're much more likely to be in contact with electric current. And so what we like to actually do is dress up the Lorentz force law in the language of currents. All right, so let's look at this. So let's imagine we have a conducting wire, and so I'm gonna have a close-up of a wire. So I'm gonna draw a little bit of a cross section of a wire, and it's really, really big. And imagine that the wire is in a magnetic field, and I'll say the magnetic field is everywhere out of the board. So I'm going to make little dots to indicate that the magnetic field is everywhere out of the board. All right, so we see that. I want to leave enough room for me to make a little drawing here. So anyway, uniform magnetic field everywhere out of the board. So again, that's like the head of the arrow coming at you. You know, when you draw X's, that's the tail feathers. That's the arrow going away from you. All right, so here's the magnetic field everywhere out of the board. And this is a conducting wire. So this is a conducting section of a wire. All right. Now in this wire, now we know we're going to say this is a conductor. So in the conductor, we know that let's just say the current, we'll imagine the electric current I is going up in the wire. So if the charged carriers are electrons, we know the electrons go the other direction. So if I have an electron right here, a little negative charge, it's going to have a velocity going the other way. All right, in this particular situation. Again, my arrows are not drawing the scale. Now let's take a look at a section of this wire. Let me kind of section it off. I'll put little dash lines to indicate I have a little section of wire that I'm considering, and I'm gonna consider a length L of this section. All right, so consider a length L, and I'm going to imagine that, okay, I'm looking at this particular one charge right now. It has a charge Q. That's not a very good looking Q. All right, try that again. I have a charge Q and has a velocity V, and it's in a magnetic field B. Great, that means that it must feel a force. So what would I write down? Well, what force does it feel? It feels the Lorentz force. So again, magnetic field is Q B cross B. Give myself some space here. All right. All right, so that is the force that charge definitely feels. Now that charge is getting pushed down. It's going down the wire at a constant velocity. All right, now I'm not going to worry right now about the vector nature of this. I'm going to actually talk about more of the magnitude. So I'm going to say that I'm going to take the hats off. That, well, the magnetic field, F sub B without the hat on, is QVB sine of theta. All right, so that is really the equation and the magnitude. Now, if I imagine, now what I'm really after is I want to actually dress this the Lorentz force law up in terms of charge. I'm sorry, in terms of current. What is a current? Well, current is the flow of charge. It's a time rate of change of charge. So if I want to dress it up like a current, what I have to do is say, well, I have I, and let's say there's an amount of charge that flows in a time delta t. All right, we're going to imagine that, you know, in time delta t, we'll say in time delta t, a charge or an amount of charge, many charges, there's many charges in these conductors. So an amount of charge Q flows a distance L. So if I'm watching the current, I would see charges come in, and I would start my stopwatch, and they would travel a distance L at a constant velocity. And as soon as I saw them get to that other marker, I would then stop my stopwatch, and that would be the delta t. All right. So now, that's a statement of the current that we've been studying, like in the last chapter. But let's kind of try to get the kinematics of this moving charge. So we imagine going back to physics 1. In fact, let's go back to chapter 2. In fact, when the simplest equation we could possibly write down is what? Constant velocity. We're not even going to worry about acceleration. We have a constant velocity. So the distance that a body travels, delta x, and a constant velocity v in delta t, that's given by delta x equals v delta t. But simplest equation to write down. What distance are we talking about? Well, we're talking about a distance of L, right? It's going to go a distance L. And so what I can do is I can actually solve for delta t. Delta t will then be what? It'll be L over v. And I'm employing the most basic equation from physics 1. Now, what I can then do is I can substitute for this into the equation for the current. So instead of writing delta t for the current, let's now replace it with L over v. Okay? And then I can clean up the algebra a little bit. I mean, real simple, just a little division. And I can say that I can write this then as I is equal to QV over L. Okay, so far pretty simple arguments. And then what am I going to do? Well, remember the name of the game. What am I trying to do here? I'm trying to write the Lorentz force law in terms of current as opposed to charge. So let me solve this equation for the charge. So Q, very simple, it's going to be IL over V. And then finally, I can substitute now for Q into the force law. And if I do that, what I quickly find out is that the force, magnetic force, will then be on direct substitution. IL over V times VB sine of theta. And V's cancel. And so what I'm left with then is that the force, magnetic force, is ILB sine of theta. Or in vector form, I could write this as the force, magnetic force, in terms of current, is IL cross B. Both of these equations that I'm boxing right now are absolutely legitimate. This is the form of the Lorentz force law that is the most general theoretical form of the Lorentz force law. That would be the charge being affected under the influence of a magnetic field, and the magnetic field, that interaction causes a magnetic force. But we also see that if you put a current, like a current carrying wire in a magnetic field, it also is deflected and it feels a magnetic force. This is absolutely empirically determined. And so this is the magnetic force on a current. This is the magnetic force on a charge. These are two forms of the Lorentz force law. I derived one from the other. Okay, this is an absolutely legitimate form of the Lorentz force law. There's nothing really else for me to say about it. I mean, I'm just redressing the Lorentz force law in another form. Let's work some problems out to get ourselves used to this new formalism. All right. So I'm going to look at OpenStax 22.31. OpenStax 22.31. All right. That says, what is the direction? of the magnetic force on the current in each of the 6 cases in figure 22.53. Each of the 6 cases in figure, this is an open sex problem and an open sex figure 22.53. Now let me remind you, we are in chapter 21 in our class in Cutnell and Johnson. If we're studying out of open stacks is already in chapter 22. So basically what we call chapter 20 was equivalent to chapters 20 and 21 in OpenStax. So again, when I'm looking at OpenStax chapter 22, this is an OpenStax problem. We are now out of alignment. By the time we hit, I think electromagnetic waves will be back in alignment again. But we're currently out of alignment with the as far as the chapters go. So these 22s are, that's just because I'm looking at OpenStax problems. All right. So I have 6 cases that I'm gonna need to figure out. I want to find a force on a current. So I'm gonna draw it up. It's very similar to previous problems that we did regarding charge. Now we're gonna look at current. So I have 6 different drawings I'm gonna put up here, and let's see what they look like. So okay, so the first one we have looks like this. We have magnetic field into the board. All right, this is a magnetic field. Sorry, not into the board. I apologize. Out of the board. These are the arrowheads coming at you. This is the magnetic field coming out of the board, and you have a current going straight down. Now, as I've said many times, first thing you want to do, again, electromagnetic theory is a very vector-oriented, is a very much a vector theory. So you want to write an orientation down. So I'm going to do that. So anything I discuss is going to be with respect to this orientation. This is positive x hat to the right, negative x hat to the left, positive y hat up in the board, negative y hat down the board, and of course I say positive z hat because the right hand rule must be effective, so x cross y must equal z. So positive z hat is out of board, negative z hat is into board. All right, that's my orientation for these next problems. Really, my orientation for probably pretty much also chapter. All right, so let me write down what I'm seeing here. So again, B is in positive z hat direction. Right, it's coming straight out at you. That's defined as z hat, positive z hat. The current is going straight down the board. The current would be in, I call it IL actually, because IL is actually your vector, is in negative y hat. So I need to find the force. So again, what is my equation? I'll just write up here on the top. The Lorentz force law for currents is IL cross B. Remind ourselves what the equation is again. That's the governing equation in terms of where the magnetic force goes. Okay, so again, a cross product must be done in order. You line your fingers up with the first vector that you read first, left to right. That's L. IL is going straight down, and where's B going? B is going out. So again, it's a little bit difficult for me to demonstrate, but IL, my fingers line up straight down, and then I know that B is going to come out of the board. So IL cross B. Where's my thumb go? To the left. Again, IL. I'm lining my fingers up with the first vector. Cross B. I know it's crossing outward. My fingers curl with the second vector, and my thumb points in the direction of the magnetic force. My thumb is pointing to the left. that means that the magnetic force is in the negative x-hat direction by the right-hand rule. And again, one way to look at this is say, well, I know I see I have three coordinates in the Cartesian system: x, y, x hat, y hat, z hat. Well, again, the z hat and y hat are already taken up. Every one of these, the force, the current element, and the magnetic field all must have their own coordinate in this particular situation. So I know that z and y are already taken, so my answer has to be something x. Well, the right-hand rule determines what that is. So my answer, this first problem, is that f sub b is in the negative x-hat direction by the right-hand rule. Okay, and I'm sorry, this is part A. So this is part A. Now, let's look at part B. New picture. So here we go. I'll keep my orientation the same. Keep my Lorentz force law up there. That's always applying. All right. Magnetic field is to the right. It's in the positive x-hat. My drawing. That's my magnetic field. And my current is straight up in the positive y-hat. All right. So what is it? Well, B is in positive x-hat direction. IL is in positive y-hat. Again, look at my orientation. All right. So I have to figure out the force. Well, again, I play the same game. I line my fingers up with the first vector, reading left to right, and I cross my fingers. I curl them in the direction of the second vector. So first vector, my second vector is going to go this way. So first vector, IL. And then I'm crossing which direction? To the right. Cross B. IL, cross B. My thumb points the way. My thumb is pointing into the board. So the magnetic force is negative c hat, according to the right-hand rule. And it takes a little getting used to this right-hand rule business. I mean, physicists are doing electromagnetic theory. Oftentimes people look at them funny because they're always doing this over their right hand, right? And so, anyway, that's what's to it. Again, I mean, again, so everybody's represented: X, Y, and Z. Everybody has a representative coordinate. All right, letter C. Draw the picture. All right, so I have now a magnetic field going into the board. So we're going to see the tail feathers. And the current is to the right. I'll draw one more set here. And then the current is drawn right like that to the right. There's your current. So all these tail feathers, they just basically mean the magnetic field is going into the board. So writing this down, well, I follow IL cross B. Let's write down what we have. We know that B is in negative z hat. Okay, I know that. And IL is in positive x hat. So IL cross B, I line my fingers up. So again, I know my B is going to go in. I line my fingers up at the first vector, reading left to right. IL cross B. B is going in. My thumb is doing what? It's pointing straight up. IL cross B. So if my thumb is pointing straight up, that means that the magnetic force is in a positive y hat direction. Okay, letter D. All right, so D is going to be a little different than the other ones. All right, so D says, let's see, I have magnetic field going in the positive x hat. and that's my magnetic field. And then I have the current anti-aligned in the negative x hat. There's my problem. Well, let's see here. I have, so I write this down. I have, okay, well, I have B, and this is where you kind of get startled here, right? So B is in positive x hat, IL is in negative x hat. So again, as I told you, one of the vectors should be, I mean, x hat, y hat, z hat. There should be representation, right? Well, I have x hat and x hat. Okay, so there's x hat, negative x hat. Well, that automatically should kind of alarm you that there's a problem or there's something different about this problem. So what it is here is that B and IL are anti-aligned. So I don't even care about the cross product right now. And honestly, what I really care about is, you know, if I look at this particular form, I have f sub b. Just look at the scalar, all right? F sub b is what? It's q. Oh, I'm sorry. It's a IL b sine of theta. What's theta? Well, if they're anti-aligned, theta is 180 degrees. So I have f sub b is I, whatever it is, LB sine of 180 degrees. The sine of 180 degrees is 0. That means that I don't have to worry about any cross product at all. The magnetic force for this situation is 0. All right, so you can't cross a vector with itself, right? I mean, you get 0 when you do that. So again, I've said this before, but in this particular case, you have them sharing the same coordinate, x hat. Yeah, they're going opposite directions, but again, if you have a vector, cross with itself, you know, like x hat cross x hat, that's 0. Or anti-aligned, x hat cross a negative x hat, that's 0. Y hat cross y hat, that's 0. Z hat cross z hat, that's 0. I mean, you have to cross a vector with something that's not in the same line as that vector, or you know, they have to be in a they can't be in the same plane basically. And yeah, you know, I'm sorry, not the same plane. They can't be in the same line. Of course, they can be in the same plane. They can't be in the same line. All right, and so these are anti-line. Cross product is 0. You know, so sine, if they're aligned or they're parallel, theta would be 0. Sine of 0 is 0. If they're anti-parallel, like in this case, sine of 180 is 0. So again, there's no real cross product to even be done for part D. All right, let's look at part E. Okay. So part E, the picture looks like this. I have B going straight up in a y hat direction. There's B. And I have the current going into the board. I have one wire, current carrying wire going into the board. There's my I. I'll just write down what I see. Well, B is in positive y hat direction. IL is in negative z hat direction. Well, again, I have representation y, z, so my answer must be something x, right? Well, again, the right-hand rule determines that. So let's see, how do I do this again? I line my fingers, again, I have to use my right hand. I line my fingers of my right hand up against the first one, reading left to right, while IL is going straight into the board. And I cross it how? Well, crossing it's up, so palms up, I guess. IL straight into the board, cross B. My thumb points the way of the force. It's to the right. So F sub B is in positive x hat direction. All right, one more part F. See what it looks like. All right. I now have a magnetic field to the left. And my current is out of the board. All right, so again, write down what I see. B is in negative x hat direction. IL is in positive z hat. It's coming out at you. Positive z hat direction. Where's the force? Well, it's going to have to be something y, right? So let's see here. Right hand rule. IL cross B, right to left. So again, IL is let's see here. It's coming at you. IL, cross it with B. So again, IL, where's B going? It's to the left. So IL coming at you, cross with B. My thumb is going straight down. IL coming at you. This is positive hat direction. Cross it with B, which is in a negative x hat direction. My thumb pointing straight down. That means that the magnetic force is in negative y hat direction. Again, you know, it takes them getting used to, but again, it's all determined by the right hand rule. Okay, let's look at OpenStax 22.33. It's another one of these vector problems. I'll keep my orientation up just like I have it. And in fact, I'm going to need to keep my Lorentz force law up there too. So again, similar problem. So it's basically saying, what is the direction of the magnetic field? Now we're going to solve for the magnetic field, not the magnetic force, but the field. So what is the direction of the magnetic field? That produces the magnetic force shown on the currents. Magnetic force shown on the currents in each of the three cases in figure 22.55. Assuming B is perpendicular to I. Okay, so I have some pictures to draw. So what is the direction of the magnetic field? We're looking for B now. So this is what we're solving for, not F. That produces the magnetic force shown in the currents in each of the three cases in figure 22.55, assuming that B is perpendicular to I. All right, so they're going to be perpendicular to each other. We're making sure that these two are perpendicular, like they did, like it was in the previous problem. All right. So what are our pictures? The governing equation is Lorentz force law for currents. All right. Part A looks like I have a current in the positive y hat direction, and I have the force in the negative x hat direction. All right, so again, as I kind of said, the force is what I have now. I have the answer is in negative x hat, and the current IL is in positive y hat. Now, I'm looking for the magnetic field. So here's the difference here in this problem is that I have the answer. remember the answer to the Lorentz force laws were my thumb points. So I can automatically point my thumb to the left in this problem. And then again, my fingers initially align with the initial vector, reading left to right. So again, I know the answer. My thumb points to the left because that's what and then my fingers are going to line up with the initial current. So that's my initial problem. My initial current is straight up and my thumb points left. So again, by the anatomy of my right hand, I mean, my hand doesn't bend backwards, it bends forward. So it's going to go forward. So so by the right hand rule, the magnetic field that must apply is straight into the board. So the magnetic field B is in negative z hat direction by the right hand rule. Because that's the anatomy of my hand. My hand doesn't bend backward, my hand bends forward. Okay, let's look at part B. Part B, I have the magnetic force straight into the board. And the current is straight down. Okay, and so let me reiterate this. So magnetic force is in negative z hat direction. IL is in negative y hat direction. All right, and so what I need to do is right hand rule. I got to find out where the magnetic field is. All right, so again, I start off with where my answer is. My answer is my thumb's pointing in. That's my answer. Whatever it is, my thumb's pointing in. However, I line my fingers up. How? I need to line my fingers up with the current. So my thumb's got to be pointing in as my answer. My current has to initially line up down. So my thumb's pointing in. The IL is pointing down. By the anatomy of my right hand, it can only bend this way. And it can only bend to the negative x hat direction. All right, and so the magnetic field is in negative x hat direction. Again, by the right hand rule. I'm solving for B now. Let's look at part C. Part C says, I have the magnetic forces in a positive y hat. And the current is in a negative x hat. All right, there it is. So what do I write down? Well, again, the magnetic field, magnetic force is in positive y hat. IL is in negative x hat direction. So again, I line my fingers up with my thumb, up with the answer. So my thumb lines up with the answer. That is, my thumb's got to be pointing up. However, my fingers have to start off with lined up with the current. So it's going to be a little bit hard for me to demonstrate this, but I have my thumb up. My hand has got to be initially to the left. So my thumb is up, but again, my thumb is the answer. That's where the magnetic force is going to be. My fingers align with the initial vector, reading left to right, the IL. All right, so by the anatomy of my right hand can only do what? It can actually bend outward toward you. So that means that the magnetic field is in positive z hat direction. Okay, so this gets a little bit out of the board. This gets a little bit, getting used to, So, all right. So those are cross product problems. So let's look at Opus X 22.34. Open stacks, 22.34. A. What is the force per meter? On a lightning bolt? At the equator, that carries 20,000 amperes. Perpendicular to the Earth's .00 times 10 to the negative 5 Tesla field. Okay, and then B, what is the direction of the force? If the current is straight up. And the Earth's field direction is due north. Parallel to the ground. All right. So let's read this again. Open stacks 22.34. A, what is the force per meter on a lightning bolt at the equator that carries 20,000 amperes, perpendicular to the Earth's 3.00 times 10 to the negative 5 Tesla field? B, what is the direction of the force if the current is straight up and the Earth's field direction is due north, parallel to the ground? So we'll do one step at a time. For real estate person, I need to erase these words here. So let's remind ourselves, keep in mind what we're doing. Okay, so part A, again, so really part A is going to give you the magnitude of this force, and part B is going to give you the direction. All right, that's really what's going on here. So what do I know? I know the current is 20,000 amperes. That is almost ridiculous. The magnetic field is 3.00 times 10 to the negative 5 Tesla. That's typical magnetic field on the Earth, surface of the Earth. We're also told that they're perpendicular. So we're told that we're told that IL is perpendicular to B. So theta, that means that theta equals 90 degrees. Okay, Lorentz force law says that, again, that the magnetic force is IL cross B. For this particular problem, we're really going to worry about magnitude. So let's take off the hats. So the magnetic force is ILB sine of 90 degrees. Because, why? Because IL and B are perpendicular. Sine of 90 is 1. Great. F sub B is I, L, B. Again, L is the length of the length of the section of the current under consideration. I is the current, and B is the magnetic field, but we want the force per length. So we'll divide both sides by L. What we're after in this problem is F sub B over L. We want the force per unit length. That's just going to equal to IB, or 20,000 amperes times 3.00 times 10 to the negative 5 Tesla. So I work that out. I get that F sub B over L, the magnetic force per unit length, is then equal to 0.6 newtons per meter. That's the force per unit length per meter. So 1 meter of this lightning bolt would experience 0.6 newtons. 2 meters would experience twice that amount, and so on and so forth. So force per unit length. All right. Now part B, we worry about the direction. So we're going to establish a little coordinate system on the surface of the Earth. All right. And so again, we're not going to really need the magnitude any longer for part B. So magnitude, if you needed the magnitude, you have it. But for part B, we're just looking at direction. All right. So we're gonna place a coordinate system on surface of the Earth. We're going to say that in this coordinate system that positive z hat is up toward sky, negative z hat is down toward ground. And then let's see here. Positive x hat is east. Negative x hat is west. Positive y hat is north. Negative y hat is south. All right, so we're establishing a coordinate system at this particular location at the equator so we can study our problem. Now, what are we told? We're told, first of all, that the lightning is straight up. The lightning bolt is straight up. All right. So lightning bolts, that means the current, IL, is in positive z hat direction since it is straight up. And you got to read the problem really carefully. Great, we know that. What about the magnetic field? Well, we're told the magnetic field at this location is due north. What does due north mean? That means positive y hat. And that means that's equal to positive y hat. All right, so the lightning bolt is positive z hat. The magnetic field is positive y hat. We want to find out which direction force is going. Well, I use the right-hand rule for that, right? So again, I go back to Lorentz force law. F sub B is I L cross B. Again, there's going to be a force, a deflection force on this lightning bolt because it is in a magnetic field. All right, so which direction is that going to go? Well, IL, straight up. I'm going to imagine this is up, this is down, this is, I don't know where east is. We're going to say this is east, east, west, north, south. All right, so again, up, down, east, west, north, and then south, right at you. All right, that's what we're going to do. So up is IL, IL is up, and then we're going to say, okay, so cross B. Well, I said that forward is north. Okay, so my thumb points what? To the left. IL, that's the lightning bolt's going straight up. Cross B, my magnetic field is heading to the north. So the deflection force is going to be along where my thumb points. That's to the left. So that means that F sub B points due west. Negative x hat means in this language due west. All right, so there's a westward deflection force on the current and the lightning bolt. Okay, let's do another problem. OpenStax 22.35. Okay, what does that say? A DC power line for a light rail system carries 1,000 amperes. At an angle of 30.0 degrees to the Earth's, so at an angle of 30.0 degrees to the Earth's uh, 5.00 times 10 to the negative 5 Tesla field. What is the force on a 100-meter section of the line? B, discuss practical concerns. This presents, if any. All right, so here we go. A, so see, OpenStax 20.35. A DC power line for a light rail system carries 1,000 amperes at an angle of 30.0 degrees to the Earth's 5.00 times 10 negative 5 Tesla field. What is the force on a 100-meter section of the line? And then B, discuss practical concerns this presents, if any. All right, so again, let's work this out. So I need space, so erase the board. All right, back to part A. All right, so let's write down what we know. We know that the current in this line for the light rail system is 1,000 amperes. We know that the magnetic field of the Earth at this point is 5.00 times 10 to the negative 5 Tesla. We know the angle between the current line and the magnetic field at this particular point is 30 degrees. So that's the angle between IL and B. L, the section of the line we're considering is L. The length of that segment or section of that current or that wire or line that we're considering is 100 meters long. Okay, so going back to Lorentz force law again, F sub B is IL cross B. All right, so we write it in terms of magnitude. It's going to be F sub B is ILB sine of theta. All right, so we want to figure out what the force is. So we're going to work it out down here. So the force is going to be ILB. So let's see, it's 1,000 amperes. L is 100 meters. B is 5.00 times 10 to the negative 5 Tesla times the sine of 30 degrees. Okay. So we work all this stuff out, we find out that F sub B will be equal to 2.5 newtons. Well, there's 4.448 newtons in a pound. We're talking about a half a pound-ish, half a pound worth of force that the 100-meter section is gonna feel, and that's, you know, again, that's not trivial. It's not great, but it's not trivial. It's enough to move the wire. You know, so it's one of the things, you know, if you watch some YouTube videos, you know, or maybe news articles, you see a big tornado that comes through and has massive destruction in some city, and knows that, well, it knocks down power lines. One of the things you'll notice about the power lines is they're dancing around. They're on the ground, they're moving around like snakes. And the reason why is you have this huge amount of current, and they're interacting with the magnetic field. So there's some moving around that's going to be caused because of that. I mean, you know, half a pound worth of moving around is enough to, you know, it's enough to, you know, for each 100-meter section is enough to move it little by little. You know, so you absolutely do not want to be near, you know, these live wires that happen to be knocked off, you know, off the telephone poles or broken by the tornado that goes through. All right, so what's the practical consequences of this? Well, part B. So again, that's part A. Part B is a few words. I'll kind of state what I said. Practical consequences will be, I say this means that the light rail power lines must be attached in order not to be moved by the force caused by the Earth's magnetic field. All right, so this means that the light rail power lines must be attached in order not to be moved by the force caused by the Earth's magnetic field. All right. Let's do another problem. OpenStax 22.39. All right, OpenStax 22.39. That says A. What is the angle between a wire carrying 8.00 amperes current the 1.20 Tesla field it is in, if 50.0 centimeters of the wire experience a magnetic force of 2.40 newtons. And B, what is the force on the wire if it is rotated? To make an angle of 90 degrees with the field. All right, open stacks, 22.39. A, what is the angle between a wire carrying 8.00 amperes current and the 1.20 Tesla field it is in? So again, angle between I and B. If 50.0 centimeters, L, of the wire experiences a magnetic force of 2.40 newtons. There's F. All right, so you got all the information you need, and what we don't know is theta. B, what is the force on the wire if it is rotated to make an angle of 90 degrees with the field? All right, so again, keep this in mind. Let's work the problem out. All right, so part A. So first of all, we got to write down what we know on problems like this. So what we don't know is the angle between the magnet IL and B. But we do know I is 8 amperes. We know L is, I'm sorry, we know B is 1.20 Tesla. So again, it's a current inside of a external field. The length of this wire is 0.500 meters, 50 centimeters. But again, we don't want to write 50 centimeters. We want to write it in terms of meters, of course. And then we know the magnetic force that is resulting of this. That is 2.40 newtons. So of course we go to, as we've seen, we go to the Lorentz force law for currents. F sub B is I L cross B. All right, so again, we're gonna look at the magnitude. Take the hats off of the magnitude. So again, that's F sub B is I L B sine of theta. All right, we're looking for theta. So that means I'll solve for the sine of theta. The sine of theta is F sub B over I L B. And of course, we want to take the inverse sine. So theta is the inverse sine of F sub B over I L B. All right, so theta, right down here, is the inverse sine. Let's put the numbers in now. We're ready to go. Let's see, F sub B is 2.40 newtons. And that's all divided by I is 8 amperes, 8.00 amperes. L, and everything has to be in SI units. L is 0.500 meters. And B is 1.20 Tesla. All right, so the inverse sine of all of this gives you theta equals, let's write it up here, 30 degrees, 30.0 degrees, nicely. So all this being equal, being the same, you have 1.20 Tesla field. The current's 8 amperes, and yet you're considering a half a meter section of that current. If your answer to the force, so the force of deflection is 2.40 newtons, then that means that the wire and the magnetic field need to be making an angle of 30 degrees with respect to each other. Now what we're going to do is we're going to imagine rotating this wire so that it's now at 90 degrees with the field. It's now perpendicular to the field. So what we're going to do now is, that's part A, so we're going to go to part B. Part B, we're going to now say, okay, part B, we're going to make theta be 90 degrees. All right, that's what theta is going to be now in part B. Everything else is the same except, of course, the force. The force is no longer the same. So we're going to be computing now a new force. All right, so now we're going to rotate this wire exactly as it is, and we have to have a new force. We're computing a new force now that's going to result from this new orientation of the wire. All right, so here's everything else is good except this is 90 degrees now. So now F sub B is I L B sine of 90 degrees. And of course, the sine of 90 degrees is very nicely equal to 1. So your force, F sub B, is I L B. F sub B is the current, which is 8.00 amperes. L is 0.500 meters. B is 1.20 Tesla. And you put it all together, you find out that the magnetic force now is double what it was, 4.80 newtons. All right, so that's that. So now we're going to have a new topic. And so, we have a new version of the Lorentz force law, one that is really useful to us because we do interact directly with currents. And so there's a very nice application of the Lorentz force law that applies to our lives quite a bit. And that's the concept of a motor. So motors are direct applications of Lorentz force law dressed up in form of a current. So what I might do is I need to open up the textbook real quick and show you a picture. So I didn't do that beforehand. So give me a moment. I need to set that up. All right, give me a sec here. I gotta bring up the textbook. I should have done that beforehand. Okay. Bringing it up. Slowly but surely. Zoom tends to slow things down. All right, so here we go. You guys, I'm not even gonna. I'm gonna redraw this picture, but if you really want to know what it is I'm trying to draw, I think looking at this illustration would be of great assistance to you, a great aid, I should say. All right, so hang on, I got the book open. Now I'm gonna go to the appropriate spot. All right, so it's coming. Come on. All right, chapter 22. All right, so one more second. Here you go. Here's the picture I want. All right, so I'm going to bring up a picture and share my screen. And then I'll try to redraw this the best I can, but at least you'll know what it is I'm trying to do. And so we're going to look at a basic motor. All right, so what you see here is a picture of a basic motor. Now, a motor is, what you see in this picture is a wire loop. Okay, and the loop has current going through it. It'll be up on the left and down on the right. So the current's going to go up and it's going to go around in a circuit. It's going to come back down. It's driving a shaft. All right, now this particular wire loop is going to experience a torque, and that's because it's going to be interacting with the magnetic field caused by these pole faces. So you see the north pole face on the left and the south pole face on the right. What you're seeing here is a basic motor. A motor is the same kind of motor that drives your car or any kind of machinery. The motor is really converting or a conversion of electrical energy to mechanical energy. And so what we're seeing here is that we're driving, so that shaft on the bottom, that's going to be driving some sort of a device that's going to operate some sort of machinery. That's your motor. And so a motor is a direct application of what we just got done studying. All right, so let me try to redraw this a little bit, and I'll explain how this works. So again, we're studying motors. So again, my drawing is not going to look anywhere near as good as what's in the book, but I'll do my best. Okay, so let me start off with, let me draw the north magnetic pole face. I'm trying to draw this kind of in a corner here so that I kind of keep this picture up for a while. All right. Again, this is part of a magnet. You don't get you of course don't get a magnet by itself. That would be a magnetic monopole. So there's more magnet back here, right? This is just the north face of a magnet. Okay. Now on the other, now what we have here is a shaft. And you're going to see a current loop. Try to make it square. Best I can. Actually, not square. We'll make it rectangular. Try to make it so that it is symmetrical as well. So again, art is not my strong point. All right, there we are. Now, on the other side will be a south face magnet. All right, just like it's in the picture. Now, magnetic field lines will go straight across from the North Pole to the South Pole, or the north face to the south face. So magnetic field lines are going to go straight across. This is a magnetic field. Okay, and that's always going to be the case. Now, we're going to have current going up the wire here, and you'll have current going up the wire on this side, around, and then down. All right, there's your current. Now, the wire, the face is going to have, we'll say, a height of L. And it's going to have a width of W. And then the distance from the shaft, the center of the shaft, my drawing looks okay. The distance from the center of the shaft to one side of this loop is going to be W over 2. Okay, now let me discuss, let's say, the top and bottom sections of this wire first. And then we'll go to what's actually important. That's the side sections. All right. So what's actually happened here? Well, imagine here. Okay. So the way this is drawn, it's not, it's all that good. But the wire. Let's imagine that the wire is going to be rotating. Let's kind of imagine it gets rotated such that the wire is looking at you. So it's angled out so that the top of the wire is actually kind of going along a line from the board to the video, or to this computer here. Now, what would the magnetic force be? Well, again, in that particular case, so B is going to be to the right no matter what. All right, no matter what in this experiment, B is always to the right. Now, if I've rotated to the point where again, I'm talking about the top section of the wire, the current in the top leg. Well, IL cross B, that means that force is going to be up. And on the bottom section of the leg, I'm going to have IL. So again, IL, in this orientation, IL becoming in now. And again, cross B be down. So it turns out that the magnetic force on the top and bottom are going to be equal and opposite. And they're going to cancel out. And so we really are not going to worry about, again, it's not really drawn very well. We're not really going to worry about the magnetic force in the top and bottom of the segment, top and bottom segments. But the reality is the magnetic or the Lorentz force F sub B equals IL cross B on the top and bottom sections of the current loop are equal and opposite and cancel out. So basically, we do not need to consider the effect or the effects on the top and bottom sections of the wire loop. So I was just saying, don't worry about it. We want to worry about the sides. I mean, there's current going through, of course, the same current that's going everywhere in this current loop. However, the top and bottom are essentially just going to cancel each other out. All right, so I'm not even gonna, I'm going to try to simplify things by kind of erasing these forces. We're not really going to consider the forces on the top and bottom of the wire loop. Just to kind of simplify things a little bit. What we want to consider are the forces on the side of the wire loop. All right, so let's really kind of worry about that. All right, so let's look at the left. Let's look at, first of all, the left side. So the left side of the wire loop, we'll say the left vertical side. All right, what's going on there? Well, the current is actually going straight up, and the magnetic field, let's say in this very picture, the magnetic field is to the right. The current and no matter what the orientation, I mean, we're going to find out there's going to be a torque that's going to be twisting this this particular wire loop around. No matter what the orientation of this wire loop is, the current on this left part of the wire is always going to be straight up. And the magnetic field in this problem is always going to be to the right. Okay, so what that means is that the force is always going to be perpendicular to that left section of the wire. How and why? That's because of Lorentz force law. Again, force is, remind ourselves, remember the Lorentz force law, seen this many times already, is IL cross B. So on this left section of the wire loop, what's the force going to be? And where is it going to be? Well, it's going to be IL, which is straight up. Again, I'm talking about the left side of the wire, just as you see it. And where is the magnetic field? IL, the magnetic field is always to the right. That means in this orientation, the magnetic force is straight in. The magnetic force on this particular current in this section of the wire is straight into the board. At this location, we have a magnetic force. I'll put little tail feathers here, straight into the board. Okay, I'll turn them a little. See it? All right, that's the magnetic force that particular section of the wire feels. All right, and so that's given by the Lorentz force law. So again, that's the force on the left. So again, the force on the left is going to be given as force magnetic left is IL B, and again, IL and B are always perpendicular. IL on this left section of wire is always up, positive Z hat, if you wish. And B is always to the right. Or call it up, I guess, would be positive Y hat. Up, positive Y hat. That current is always going to be positive Y hat. And look, I'm using the wrong hand. Positive Y hat for that current. B is always positive X hat. There's always going to be there's a force that's pushing that particular left section of the wire into the board. Okay, so in negative Z hat direction. What about the right side of this current? Well, again, the right side, the current is actually going down. So the current is going down, IL, but the magnetic field is to the right. So IL, I have to stand up to show this. So again, the current on the right side is going straight down. That's IL, straight down. The magnetic field is still to the right. So now the force is pointing straight out at you. Positive Z hat. Okay, and so again, right hand rule. So I have equal and opposite forces. So this force on the right hand side of this right section of the wire is coming right out at you. So F sub B on the right is ILB. Again, this current is always straight down. This particular section of current, this particular section of wire is always going to see a negative Y hat current. And again, in this particular situation, B is always positive X hat. So again, I'm going to be seeing a mutually perpendicular force. The force is always going to be basically pulling this, this wire. So ILB in this particular case in the positive Z hat direction. All right, so just like before, the forces are equal and opposite. So F sub B left is equal and opposite to F sub B right. But here's the kicker. They exert torques. And let's take a look at what the torque does. All right. So again, we got to go back to, so again, we have forces, no doubt about that. I showed that to you, and they're equal and opposite all the time. The force on the left vertical section of the wire is always equal and opposite to the force on the right vertical section of this wire loop. But here's where things get interesting. These two forces both exert torques. Let's remind ourselves now about the torque. Let's go back to physics 1 for a moment. Remember my, so those of you who have me for summer class, remember my example of pushing the door open at Starbucks? I have a door hinge. I'm looking at it straight from the ceiling on in, and I'm seeing, you know, a door. And let's say this is the, you know, this is the top of my head, and here, you know, my front of my eyes, whatever. I'm heading toward the door, right? You're seeing the top of my head. We're looking from the ceiling. So here's the door hinge going from the ceiling down to the ground. Here's the door. Now I have the, so I can essentially, you know, I can apply a force to this door any way I like. So let's just say in general, apply a force vector. Let's say, and let's say this way, this is my force vector. And of course, you know, the distance from the rotation axis to the application point of the force is called the moment arm. That's also a vector. Call that R. And there's not a very nice drawing. Try this again. Again, the moment arm has to go straight from the center. That's R. And there's an angle theta between the force and R. So what's happening here is when I open up the door, I'm applying a torque. And again, as a reminder, the torque is again what? It is another cross product. R cross F is the torque. All right. So if R and F are in the plane of this board as drawn, the torque is either going to be straight out of the board or into the board. And where's the torque going to be? It's going to be about the rotation axis. In this particular case, my torque is going to be about the hinges, and it's going to be what? It's going to be a counterclockwise torque. All right, and how would I work this out? Well, I would say that the magnitude of the torque, like I would in any cross product, is the magnitude of the moment arm times the magnitude of the applied force times the sine of the angle between the moment arm and the force. That is my torque. Okay, now applying this, let's just talk about the right hand torque. All right, let's talk about the torque. I'm going to start off with the right side of my right vertical leg, all right, of my wire. And let's kind of see what that looks like. So again, I want to say the torque on that, as I said, is R F sine of theta. What is theta? Theta is the angle between R and F. All right, what's F? Now here's the beauty, right? The complicated part of this problem is there's actually a cross product within a cross product. All right, so the force, the magnetic force, is obtained via a cross product. However, that's an easy cross product. Remember the magnetic force, we'll consider this the magnetic force now. Well, the magnetic force, as I've said many times, is IL cross B, but IL, depending upon whether you're talking about the right or the left wire segment, is always, I'm going to talk about the right wire segment, is always along negative y hat for right vertical section of wire. And B is always, in this drawing, B is always in the positive x hat direction. So B is always in the positive x hat direction. So don't get confused about all the cross product stuff. The one for the magnetic force is easy. It is always, IL and B are always vertical, or always at right angles to each other. the angle between IL and B throughout this entire problem, no matter what the orientation, it's going to be 90-degree angle between them, no matter what. That means that I will always have ILB sine of 90 degrees. Sine of 90 is 1. That means that I will always have a force in this problem of ILB. So again, don't worry about, the only cross product you really have to worry about in this problem is a torque. All right, so I can literally just sub this in here and say, okay, well, fine, I have tau, and I'm looking at tau sub right, looking at the right vertical section of this wire. Tau sub right is ILB. I'm sorry, RILB, sine of theta. So tau sub right is RILB sine of theta. This theta is the angle between the moment arm and the force. Now, so again, I don't have to really worry about the cross product that leads to my magnetic force. What I do need to work, so what is the moment arm right now? Again, I'm applying a force on, let's say, the right section of this wire. Well, if I look at the shaft, there's a rotation shaft right down the middle. And again, as I said, I'm rotating about the middle of this wire loop. I'm rotating at a distance of W divided by 2. If I understand that this width is W. So what I can write now is I can say, well, tau sub right is going to be W over 2 ILB sine of theta. Okay, that's the torque that's going to be felt on the right section of this wire. Okay, now there's 2 sections of the wire, right? By symmetry, I could do all of this physics again, and I would find out that tau sub left is also equal to W over 2 ILB sine of theta. So there's a torque, and the 2 torques are doing this, and they're basically helping each other. Even though the forces are equal and opposite, the torque on the left wire is pushing this wire in, and the torque on the right wire is pulling it out. They're both contributing to twisting it around, basically in a clockwise direction. They're contributing to making a torque that's going clockwise. Both of them are helping with an exact same way to create this torque. This clockwise torque is twisting it about the center of the shaft, which means that the total torque being applied on this system, on this loop, will be tau right plus tau left. Or the total torque, adding it together, these 2's go away because 1/2 plus 1/2 is 1. So I have WILB sine of theta. Okay, I want to show you some pictures now. And so, and again, I'm showing these pictures because, and I'll try to draw them out a little bit after I show them. But again, the artist in this book does a much better drawing job than I could ever do. So let me go back and share the book. And again, this book is open access. I've been meaning to send it to you. I need to send it to you. Let's get very busy. All right. So I'm going to share my screen again. All right, let me move down a little bit in the book. All right. Oops. I wanted to show you. Oh, goodness. All right. I'll use the scroll bar, I guess. All right. So I'm going to show you a series of pictures. Okay. So look at the upper left picture. There's going to be a series of 4 pictures here. It's having a hard time navigating this thing. All right, so let's look at picture A. So picture A, let's kind of give us an orientation here. It is us looking at the wire loop from the top. We're looking at it from the top. All right, so we're looking down from the top of it, and so we're seeing one of the vertical wires. We'll say the one on the right is one we're focusing on. Is actually those tail feathers, the crossbuck there means into the board, into the page, and of course the current will go into the page and that section of wire will come down, go around the bottom, and it'll come up on the other side out of the page, and then it'll come across the top, and it'll keep doing that, right? So again, we really are concerned about the side sections of the wire, and we're really particularly focusing on the one where the wire is into the page. Now, notice a couple things that are very interesting. So we see that we have the center of the shaft. We see that there is a torque that's being applied about the shaft. We see that from the center of the shaft to this particular wire of interest, the section where it's vertical and going into the page, the distance is W/2. That's the moment arm. Now, interestingly enough, as I've said many times, this particular section of wire will always be going into the page. It'll always be going perpendicular to the magnetic force. So in this particular case, into the page might be Z hat. The magnetic field is going to be to the right, or X hat. So the force is always going to be down. It's always going to be along negative Y hat for this wire. Okay, so again, that's always true. The current IL is always going to be down in this section of the wire. It's a vertical section of the wire. Magnetic field, as is set up in the problem, is always to the right, always positive X hat. And so the magnetic force, you'll see consistently from, across these various pictures, is going to be straight down the negative Y hat direction. Now, as you can see, that vector is pointing straight down. That is the force. It is exhibiting a torque. The torque is clockwise in this picture. All right. So what's happening here is the first picture, you see an angle theta. The angle theta is the angle between the force and the moment arm. And this takes you a little geometrical convincing, but that's also the angle between the normal to the face of the current loop and the magnetic field. So imagine if you're as you're looking, you see that dashed line with the theta that with respect to the field. Well, imagine that you have an eyeball that's essentially looking. Let's see if I can get my mouse over here. You're looking right over here. You're looking at the face. And so again, the normal to that face of the loop, the normal of that face with the magnetic field is also theta. Okay, so that's picture A. Left to its own devices, what's this system going to do? Well, it's going to actually rotate to the right. And if you look at picture B is a special case where it's been rotated such that the actual top of the top wire and the loop is actually now parallel to the magnetic field. In this particular case, we have the current still going straight down. Now, when you see the magnetic force is actually going to be going straight down. It's actually going to be a 90-degree angle with the moment arm. So again, that's actually the max. Remember, there's a sine of theta right there. Sine of 90 is 1. So that's the maximum value that will be, the maximum torque will be experienced. The torque varies with theta. The maximum value of theta will be experienced in this particular, in this revolution is when the angle between the magnetic force and the moment arm is 90 degrees. We now go to picture C. Again, we're still letting this loop rotate. We go to picture C, and we see another special situation. We see a special situation where the normal of the face is now parallel to the magnetic field, or the top wire in the loop is actually perpendicular to the magnetic field. In this particular case, you see the force. The force is still going to be in that wire that's going into the board. That's now down at the bottom in this orientation, been rotated down to the bottom. The force is still going to be going straight down. It's been going straight down the entire time. But now the angle between that force and the moment arm is now 0. In fact, the moment arm and that particular force are now aligned. In this case, the sine of 0, theta is 0, the sine of 0 is 0. There is no torque. Notice there's no torque being drawn in the diagram part C, the part C diagram. Now, the system goes past that particular configuration C, goes to this configuration D. Now, of course, the force on that wire, again, that section of the wire that we've been watching, the one that's has the tail feathers where the current is going into the page, that force is of course still going to be going straight down. But this time, notice something very interesting. In the past, the force going straight down has had a tendency to do what? So let's kind of look at a earlier picture. Like you take a picture, you take part A. The picture in part A, that force would cause a clockwise torque. It would really have the effect of turning that wire clockwise. It'd be pulling down on the wire. In picture D, now that effect of pulling down is actually now causing a counterclockwise torque. The sense of the torque has now been reversed. In fact, if you were to let this system, go on, it would actually oscillate. You'd have clockwise torque thing, counterclockwise torque thing, clockwise torque thing, counterclockwise torque, and so on and so forth. To prevent that from happening, I'm going to write a lot of this stuff down on the board here, but there's a special device that's essentially an automatic periodic switching device. So it switches the currents periodically, and that device is called, and those devices are called brushes. Brushes actually will cause the periodic switching, such that you just get one sense of torque, not this oscillation behavior. The oscillation behavior is not going to do you any good. You need to have brushes to allow you to actually have a motor that actually drives the shaft. All right. So let me kind of state this here on the whiteboard. I mean, the best thing to do is to show these pictures. They do a much better job than I do. Now, I'm going to erase the main picture. I think we got the idea on this main picture. Let me put the main equation that I derived in the parking lot. We're actually gonna make this equation look a little bit different looking in a minute. But let's erase this main picture, and I'll put the torque equation for this motor. I'll put it in the parking lot up here on the top. So I'll say, okay, tau is WI/LB sine of theta. Now, let me kind of redraw some of what I just showed you. All right. So the initial picture that I showed you, again, we're looking straight on at the loop from above. And so what we see is on the top, you saw the part of the wire that's going into the board. All right, so it's going into the board, and then that's being connected, across. Here's the shaft, and on the other side is the part of the wire that's coming out. There's a current coming into the board. That current goes all the way down to the bottom of the wire, goes across the bottom, comes back up this side, and then comes up this side and then crosses the top. Okay, so again, you're looking at the top version. This section is the current that's going in. This section is the current that's going out. All right, as we said, the magnetic field is always to the right. All right, so that's always happening. So again, if well, let's focus now just on the like they do. Let's focus on the part of the wire, the section of the wire, the vertical section that's actually going into the board. Well, again, what's the force going to be? Again, I look at my right hand, IL going into the board, cross B to the right. That force is going straight down. As you always saw, that force was going straight down. That is the magnetic force caused by the Lorentz force law. Okay, the angle, this is the moment arm that we saw in there. This is W/2. And so the angle between the moment arm and F sub B, the force, is theta. As we see that there is a tendency, and again, you're going to get what? On the other side, you're going to get another force. What's it going to be? Again, it's going to be, let me see my fingers here, IL coming at you, cross B, it's up. So it's going to be a force that's going to go straight up. Draw it nicely. And that's the first picture that we saw. All right. Now, what's the tendency of this system to do? Well, this force wants to yank it down, wants to rotate it clockwise. This force wants to pull it clockwise. So the overall torque in the system, the sense of the torque, is to go clockwise, as we saw. So this thing's being rotated clockwise. And then you saw a picture, your next picture, this is picture A. Okay. Then you saw picture B, where we take a spot in time where now the wire, the top wire is now parallel to the magnetic field. And again, if I'm looking at the loop from the side, and so my eyeball is over here looking at it from the side, I mean, there's going to be a normal to this area. And again, as I said, that normal is going to form an angle theta. That's the area normal. That's going to form an angle theta with magnetic field as well. And again, convince yourself of that, kind of look at the geometry. So the normal to this space is also going to form an angle theta with magnetic field. I'll explain why that's important in a minute. All right, so we're going to look at a later time. This wire loop is rotated such that the top wire is now parallel to the magnetic field. So I'm going to kind of redraw picture B. So again, my magnetic field is always to the right in this picture. And now the part of the wire I'm most concerned about is the part that's coming, the vertical section is going into the board. Well, it's now moved over to be lined up, and here's the center shaft. Come back over here, and here is the part that's in. And again, the current's going in. This is a magnetic field. You're always going to have the magnetic field, the magnetic force going down. Again, you're still going to have IL cross B straight down, as usual. Magnetic force is going to be consistently straight down in this picture, and on the other side is going to be consistently straight up. And that's just because these currents in the side wires are always going to be along the Y direction, either out or in, and the magnetic field is always going to be in the X direction. So you're always going to have, back it up. The currents, the side currents are always going to be in the Z direction, plus or minus, and the magnetic field is always in the positive X hat direction. So you're always going to have magnetic forces directed in the plus or minus Y direction. Okay, so that's consistently, you're going to see that. Now, what's cool about this picture now is that, well, you now have the magnetic force and the magnetic field. They are now perpendicular to one another, right? And so what you now have is that theta is now 90 degrees. So in this particular case, you have tau is ILB sine to 90 degrees, which is the largest value that that theta can take. So sine of theta is 1 now. So this is actually the maximum torque. Tau max occurs when the magnetic when essentially when you have angle theta equals 0. So the force and the moment arm are now aligned. All right. So again, we're talking about here. Moment arm is again W/2. So that's what I'm talking about. They are aligned. The moment arm and the force are aligned. I'm sorry, not aligned. I apologize. The moment arm is perpendicular to the force. All right. So again, tau max is ILB. Sine of 90 degrees is as big as you're going to get. So here is any old angle theta between the force and the moment arm. Now we have a special situation. Here's the moment arm. Here's the force, the torque, the angle of the torque. Now this is theta. Theta is 90 degrees now. The angle between the moment arm and the force. And this is the torque. It's still, again, it's still clockwise. We allow the system to continue rotating, and part C showed another special picture. And that picture was we continue rotating this wire loop, and we get this special section now where here's my shaft. Now this part of the wire that I'm interested in, the one where the vertical wire where the current is going, and has now rotated down to the bottom. And the top, the other side of the wires come in out of the boards. Again, these are still the currents. And now let's take a look at what's going on. Again, it's supposed to be a symmetrical picture. Magnetic field is still going to the right, as always. But now, what do we see? Well, again, the force is always going to be down for this particular section of the wire. That's because of the Lorentz force law. Again, consistently, it's always down. And the magnetic force consistently on the other section of the wire that's coming out of the board, that magnetic force is consistently up. But let's look at this. This is now the moment arm. And the moment arm in this arrangement is aligned. Now the moment arm is aligned. So now theta is 0. At this point, F sub B is aligned with the moment arm. In this case, what's the torque? Sine of theta. Sine of 0 is 0. In this particular section, the torque is at its minimum. It is 0. There is no torque. There's no torque vector to even write down. There's no sense to write down because there is no torque in this particular configuration. The moment arm and the force for this torque equation are now aligned. And now we allow the system to continue moving. And now it gets to a point where it's gone past 0. It's gone past 0. And the last picture that they drew was the following. Now the torque has gone past 0. All right. So now that section, here's the shaft. Now that section that we're concerned about of the magnetic, of the current going into the board has moved over here. And of course, the other side is over on the other side here. That's the current coming out of the board. We're kind of watching the current going into the board. We're watching that section. Again, here is the moment arm. That's our R, if you will. And of course, the force on this section, this vertical section of wire that's going into the board is always straight down. Again, that's according to the Lorentz force law. That's been the case every single picture I've drawn up here. And the magnetic force for the vertical section of wire that's coming out of the board, that's always straight up. Again, that's been consistent with every single picture I've drawn. All right, now what happens? Something very interesting, as I said. Now, in this picture in part, this is picture A, this is picture D. Picture A, remember, the magnetic forces did what? They had a tendency to twist the loop clockwise. What's this have a tendency to do? This has a tendency to pull the loop counterclockwise. So once it goes past 0, the torque now reverses. it now becomes counterclockwise. And as I said earlier, if this system was left to its own devices, it would just oscillate. Clockwise, counterclockwise, clockwise, counterclockwise, clockwise, counterclockwise, on and on and on. It would just continue oscillating back and forth, and that wouldn't be a very useful motor to us. All right, so what we actually have to do to make a motor, we have to employ switching devices that are called brushes. So they actually make a motor, essentially left. So this system will oscillate back and forth. As the sense of the torque periodically switches. Clockwise to counterclockwise to clockwise, etc. Okay, that kind of behavior is not going to make for a good motor. All right, and so essentially, you'll hear about this if you go have your car taken in, to have it fixed sometimes, and it's a motor problem. You'll sometimes hear them talk about what are called brushes. So to get the coil to continue rotating in the same direction, we can reverse the current as it passes through theta. So we periodically reverse the current. As it passes through theta equals 0. With automatic switches called brushes. So using automatic switches. Called brushes. If you don't have brushes, you don't have a motor. All right. So again, we make a motor. We have to do periodic switching of the current over and over again, so we don't have this oscillatory behavior of the torque, going back and forth all the time. Okay. Now let's fix up this picture a little bit more, or this equation a little bit more now. So, remember in your mind what the picture looked like. Now I'm just gonna kind of move some variables around a little bit. So I'm gonna start off with what we have here. I'm gonna put W next to L. So I'm gonna say tau is I WL B sine of theta. And remember, the loop was a rectangle of width W and length L, so it has an area. Area is W times L, right? It's the area of a rectangle. So I can fix this up by saying, well, this is the same as tau is IA B sine of theta. Now, it's a little trick that's used in and currents or circuitry is that we can actually have multiple turns of wire. So what I can actually do to make things stronger is, okay, let's say I start off and I have my shaft and I have one turn of wire. Well, that's going to give me one torque, one IAB sine of theta. I can do better than that. Let's double it up and give myself another turn of wire. Okay, now I have two. Now I've doubled it. Two IAB sine of theta. Let's do it again. That's a third strand of wire. 3, 4, 5, whatever. If I have n, these are called turns. And each turn of wire is kind of like the solenoid we talked about. Actually, we haven't talked about solenoid yet. Solenoid's at the end of the section. Each turn of wire carries current I. And it contributes a torque of tau equals I A B sine of theta. Well, if I have n of these turns of wire, let's imagine I have n turns of wire. I have n turns of wire, which means that I will just fix up my equation by just multiplying it by n. So if I have a motor that has a current loop, that has n turns of wire, it carries a current I. Has an area of A, and again, I talked about the area normal. Remember in that picture I talked about drawing out, a normal. Well, that's what's important. A normal, area normal also forms an angle theta with the magnetic field. And it's in a magnetic field B, I get my the torque for the motor is given by this. This is really the final equation for the torque on a wire loop inside of a motor. So it's tau is NIAB sine of theta. Now, if I want to maximize the torque, I make the sine of theta go to 1. So tau max. So again, the tau max would then be sine of theta is 1 or 90 degrees is theta. It's just NIAB. Okay, there's your tau max. All right, let's work a few problems here to get ourselves comfortable with motors. Okay, OpenStax 22.42. That says A, what is the maximum torque on a 150 turn square loop of wire 18.0 centimeters on a side. On each side. That carries 50.0 amperes of current in a 1.60 Tesla field. And then B, what is the torque when theta equals 10.9 degrees? All right. Let's see, 20.42. A, what is the maximum torque? Okay, we want the maximum. So again, that's going to be theta equals 90 degrees. Sine of 90 is 1. What's the maximum torque on a 150 turn square loop? That means cap in equals 150 of wire, 18.0 centimeters on the side. So it's a square. So it means length and width are the same. That carries 50.0 amperes of current in a 1.60 Tesla magnetic field. So again, I is 50.0 amperes. The magnetic field in this arrangement is 1.60 Tesla. Then we want to find out what the torque is when we pick another value of theta of 10.9 degrees. All right, I want to make a quick statement before we start this problem. And I didn't say this, I meant to say it. When we did this problem, we derived the motor or the torque equation for a motor assuming a rectangular current loop. Of width W and height L. I state without proof that this motor torque equation tau equals N I A B sine of theta is valid for a current loop of any shape. All right, so that's not, again, that's not obvious. That's a more, maybe a more general typical calculation to do. But I derived it very easily with considering a rectangular current loop of width W and height H. I'm sorry, height L. However, it is actually true for any shaped loop. So it could be a circular loop. It could be a weird shaped loop. As long as it's a current loop, this equation is good. Okay, so just to let you know. All right, so again, that's a statement. I state that without proof. The proof would be well beyond the mathematics of this class. I'm not even going to try. All right, so going back to 22.42, what do we have again? So we know that N is 150 turns of this loop. All right, we know we're also told that it's a square loop. So that means the area is going to be S squared, or again, it's of side 18 centimeters or 0.18 meters on a side. We want to go straight to SI, meters. The area of this loop, of this square loop, will be 3.24 times 10 to the negative 2 meters squared. Great. We're also told that the current running through this loop is 50 amperes. We're also told the magnetic field in this arranged of 1.60 Tesla. All right, so that's a laundry list of stuff we're told. And of course, you know, we go to our torque equation. The torque is NIAB sine of theta, and we want the maximum torque. That's what we're told. We want the maximum torque. So tau max, remember, is when theta is 90 degrees. NIAB sine of 90 degrees. That means that the angle between the moment arm that I drew, or that basically the distance from the force location from the axis of rotation, that moment arm and the magnetic force are 90 degrees. All right, and so in case when that happens, that's the maximum torque that will be experienced. The torque again varies from 0 to NIAB. You want tau max? Well, basically it's NIAB. Let's plug our numbers in. So N is 150 loops, 150 turns. I is 50 amperes. A is 3.24 times 10 to the negative 2 meters squared. B is 1.60 Tesla. I find out that the maximum torque is actually going to be 389 Newton meters. Now, again, I said this back in Physics 1, but I'll say it again here. When you're talking about torque, so when you're talking about energy, you might get confused sometimes to go, well, wait a minute, Newton times a meter, isn't that a joule? Well, it's a joule if it's an energy. This is not a joule. This is a torque. A torque is a vector. An energy is a scalar. Very different. When you're talking about a torque, it is Newton meters, or English units would be foot-pounds. You're talking about torques here. 389 Newton meters. Now I'm gonna cheat a little bit here. So again, that's tau max, what I know is NIAB, and I'm gonna parking lot this answer. Again, this is my answer for part A. I'm gonna put this answer in the parking lot. All right. So remind myself. So let's put this in a parking lot. Tau max is NIAB, which I just discovered is 389 Newton meters. That's as big as a torque will get in a given cycle. All right. Now, I want to know at this point, I want to know what is the torque when the angle to the moment arm and the force, magnetic force, is theta equals 10.9 degrees. I want to know this for a particular angle now. That puts me into part B. So what do I do? Well, I go to my torque equation. Torque is NIAB sine of theta. Hey, look at this. NIAB, isn't that tau max? Yes, it is. I can rewrite this equation as, if I know this number, I can write this as tau max sine of theta. I don't have to go off and do this calculation again. I already know tau max. I know how big it gets. So in this case, tau is the tau max that I calculated in part A, 389 Newton meters, multiplied by the sine of 10.9 degrees. And I find out that the torque, when the loop is oriented in such a manner, is going to be 73.6 Newton meters. So it's, of course, it's less than the max. All right, so when the angle between the moment arm and the force is only 10.9 degrees, the torque goes down from 389 down to 73.6 Newton meters. All right, let's do another problem. OpenStax 22.47. All right. Let's see, a proton has a magnetic field due to its spin on its axis, so it's a spinning charge. All right. The field is similar to that created by a circular current loop. Of 0.650 times 10 to the negative 15 meter radius in radius. And let's see here, with a current of 1.05 times 10 to the 4th amperes. No kidding. All right. Find the maximum torque. On a proton. In a 2.50 Tesla field. Sticking in a 2.50 Tesla field, pretty strong field. And it says in parentheses, this is a significant torque. On a small particle. All right. All right, 22.47, open stacks. A proton has a magnetic field due to the spin on its axis. So it's a little tiny particle spinning on its axis. So it's a spinning charge. So it's basically like a moving charge. The field is similar, so it's isomorphic, to that created by a circular current loop that's 0.650 times 10 to the 15 meters in radius with a current of 1.05 to 10 to the 4th ampere. So this basically spinning charge, you can think of it as being isomorphic to a current loop, a very, very small current loop of this radius with this current. All right, so instead of the spinning proton is just like if you had a little current loop where the radius is very, very small, 0.650 to 10 to the 15 meters, about the smaller than a nucleus, and has this over 10,000 amperes of current going through it. All right, so and we're going to stick that proton, we're going to stick this system into a 2.50 Tesla magnetic field. We're going to figure out what the torque is on that proton when I do that. All right, so and we want to know the maximum torque. So let's write down what we know. So in this particular special case, we would consider the number of turns. If this hypothetical current loop was a wire, it would be 1 turn. All right. The current is 1.05 times 10 to the 4th amperes. The area is pi r squared, right? Or the area is pi, and we said that the radius of this hypothetical or isomorphic current loop, circular current loop, is 0.650 times 10 to the negative 15 meters. And I got to remember to square that. So the area of this current loop is 1.327 times 10 to the negative 30 meters squared. Very, very, very small. And I'm going to stick it in a pretty strong magnetic field of 2.50 Tesla. You experience a magnetic field like that, you want to make sure your credit cards are someplace else. They'll be wiped out. All right. So what's the torque equation? We imagine this being like a little tiny motor. Well, the torque equation, of course, is NIAB sine of theta. And I want the maximum torque. So again, that's tau max is NIAB sine of 90 degrees. 90 degrees, sine 90 degrees says again, 1. So tau max will be NIAB. Tau max, more room, so I'll do it down here. N is 1. I is, again, this current is 1.05 times 10 to the 4th amperes, very, very large current. A, very small area, 1.327 times 10 to the negative 30 meters squared. And B is 2.50 Tesla. All right, and if I do all this, I find out that tau max, I work all this out, I find out it's 3.48 times 10 to the negative 26 Newton meters. My little tiny subnuclear motor. Okay, so we're developing, so next topic, we're developing an electromagnetic theory. And as I said, we start off by studying what seems to be a separate field called electricity. Then we start talking about magnetism, and now we're seeing that there's a relationship now between electricity and magnetism. We see that there is a relationship between current and magnetic field. All right, now, as I said earlier, there are 4 Maxwell equations and the electromagnetic force law. We're at a point right now where we now have the electromagnetic force law in hand. I wrote it up earlier. And we also have one of the Maxwell equations, that's Gauss's law. We're now ready for the second Maxwell equation. All right, and so let's kind of motivate why we need one. So let's go back to electrostatics. In electrostatics, chapter 18 of this class, beginning of the semester, electrostatics, the central question is, given a charge distribution, what is the electric field? At some point in space. That is the fundamental question that we want to answer. So in general, what I want is I want to say, okay, I have some charge distribution, rho of r. Okay, that's some charge distribution. set of charges, continuous most likely. And I care about some location out here. And I want to know what is the electric field here. And this is a distance r vector away from this charge distribution. I'd like to know, maybe we'll consider this charge distribution from the center of mass. All right, I want to know what the electric field is there. I want to know what is the electric field at some point out here in space. All right, that is the fundamental question. And initially I don't know how to solve that problem. So what do? Well, I start off with a charge distribution that I do understand from Coulomb's law, and that is I look at and say, well, I do know this. I do know a simple charge distribution. That's a single point charge. And if I want to know what that is, let's say some point r away, well, I know how to figure that out, right? Coulomb's law tells me that E equals K cap Q over R squared. And so that is, and of course, that is in the r hat direction. That means it's a radial electric field. So I have a charge, and there's an electric field, and it's radial, and it's given as K cap Q over R squared. So I have a relationship between the charge, basically the charge distribution, which is the simplest one possible. That's the point charge, and the electric field that emanates from that point charge. I know that exactly, and I get that from Coulomb's law. So I have this very special simple case. But the question is, that's the simple case. This is only for a point charge. So I said, well, okay, I really want to solve this problem. Well, then we have to use Gauss's law, right? So we have to go to Gauss's law and say, well, okay, I have to take this particular region and divide it into little tiny areas, and each area is going to have an area normal A sub I, and electric field coming out of it E sub I, and Gauss's law tells me, says, okay, well, I have to sum up over all these little tiny area patches, E sub I dot A sub I. I have to sum over all these little area patches, the dot product of the electric field and the area normal. I sum up over, calculate dot products over, and do this over a Gaussian surface. I put a little surface, a little skin all the way around my three-dimensional object. And again, I refer to that as a Gaussian surface. And so I perform this dot product calculation. Basically, it's a flux calculation. This is an electric flux, as you will. I perform this calculation. I divide my surface into little tiny differential areas. Each one of that's electric field going through. I calculate all around these areas, and I get the left-hand side of the equation is the sum of total flux through the Gaussian surface. And by a miracle, the right-hand side says that's equal to the charge enclosed in the Gaussian surface divided by what's called the permittivity of free space epsilon naught. So that is how you solve. In general, if I have a charge distribution and I want to find the electric field at some point in space, I, in general, have to employ Gauss' law, which is the first of the four Maxwell equations. Most of the time, that's very hard to apply. The only time you have a hope of really getting an answer out of Gauss's law is in cases of high symmetry. And I showed you in chapter 18 how you can take a spherical conducting charge distribution and at a located distance r away. And I showed you how that is exactly Coulomb's law. You can actually derive Coulomb's law from a charge conducting sphere. Okay, I showed you that. And again, a sphere is a geometry of very high symmetry. All right. So now we're in magnetism. And so we're being forced with the same kind of a question. However, our question is as follows. The central question for magnetism. Well, it is given a current distribution. Remember, magnetic field is now related to current. Electric field is related to charge. Magnetic field is related to moving charge. Given a current distribution, what is the magnetic field at some point in space? All right, and so again, well, I'll draw a little picture. What do I, in this particular case, I have a set of currents. So, let's say I have, I have a current, I don't know, going into the board. I got a wire going into the board, another wire coming out of the board, another wire coming into the board, so on and so forth. And I want to take this current distribution and say, well, somewhere over here, I like to know at some distance r away, I'd like to know the magnetic field. I have a distribution of currents. I'd like to know what is the magnetic field here. And again, well, how do you do that? Well, let's start off as simple as we can. Again, with the electrostatics, we started off with the charge. So what do we do? Well, instead of a distribution of currents, let's consider a single current and see what we get from there. So a couple of French scientists by the name of Biot and Savart attacked this problem. So we're going to now look at the law of Biot and Savart. We're starting off simple, kind of like Coulomb did. And then we'll give the Biot and Savart. Law of Biot and Savart is not the second Maxwell equation, by the way. It's we're building ourselves up to the second Maxwell equation. So law of Biot and Savart. So what is that? Well, first of all, we want to consider one current. Let's make it general. So let me try to draw my little picture here. So I'm going to make a general looking current. All right, so it's going to be some calculus notation in here. I apologize for that. But let's let me make this a little bit longer. All right, so I have this current, and this current is going to have a current. This circuit is this wire, single wire, one wire, is going to have a current I in it. Okay, so there's a current I flowing in this wire. Now, I am going to pick some little section, some really differential section of this wire. And I'm going to display it like it is. So I'm picking this little thing, and I'm going to basically call this, a little displacement vector ds. And ds is a differential means very small, smaller than delta, differential displacement vector. So this section of current then becomes IDS. So current times the displacement, IDS. That's a little section of current right there that I'm considering. And I want to ask the following. So I'm going to try to draw here a little axis for this little tiny section here. This is kind of a reference axis. And I have a question. I'd like to know what is the magnetic field out here at B. I'm going to find out what little bit of dB, differential magnetic field contribution, happens at a distance r out here. We'll say this is a distance r, and that this little displacement, this little vector here, this r, is at an angle theta with respect to this reference axis. So I want to know, I have a little tiny bit of current element, and what contribution does it make? Out here in space, a distance r at some random, I'll call it a random point P. All right, I want to know what contribution that little tiny differential segment of current makes. All right, and so this is, so essentially, Biot and Savart studied this problem. And they very carefully understood that that little bit, again, remember that what the D means? I could say delta B, right, normally, but I'm going to let delta get so infinitesimally small that, that it approaches 0. And then we're going to say it's a differential B. It's a calculus notation. The little d basically means a very, very small infinitesimal delta. All right, that's really what it means to us. Okay, the law of Biot and Savart says that at this little location B, the little bit of B, little bit of magnetic field you get from a contribution of this little bit of this little current segment of the wire is given by mu naught over 4 pi IDS sine of theta divided by r squared. This is the law of Biot and Savart right here. It tells you that for some differential current element in this wire, the generalized wire, so this is a generalized wire. And I drew it about as generalized as I could. Now, this is a very difficult calculation to do. It is saying that, so you imagine this little tiny bit of, this little tiny current element is going to contribute at a distance r, at an angle theta with respect to this reference axis, it's going to contribute an amount dB, little differential amount of magnetic field, dB, at a point P in space. Now, I want the whole magnetic field. How do I do that? Well, I have to add up I have to divide this wire into little tiny differential wire elements, each one, and add them all up. But here's the complication. Every one of them is going to have its own R and its own theta. Every one of them. So I have to add all this up, and you basically do it the calculus style. You know, when you add, you do it the calculus style. So you do something like this. You say, well, when I add something, I do what's called an integral calculus. And I'd be mu naught over 4 pi I ds is my differential element, sine theta over r squared. But it's complicated because there's a lot of variation. There's a lot of variables that change here with respect to the orientation. You know, again, as you add up all these little tiny differential elements of current elements, every one of them has its own r and its own theta. So this guy would have its own r and its own theta. A current element over here would have its r and its theta. Up here, its r and its theta, and so on and so forth. All of this stuff, and you have to add up all these little tiny differentials of current elements to finally get the total magnetic field that would be located at point P. Okay, this is a very hard calculation to do. So, like many of these calculations, now I may make one quick statement. You might be wondering about what mu naught is. Left that out. Mu naught is a special constant of the universe, by the way. Mu naught is equal to 4 pi times 10 to the negative 7 Tesla meter per ampere, and has an approximate value of 1.26 times 10 to the negative 6 Tesla meter per ampere. This is called the permeability, not the permittivity. The permittivity is epsilon naught. This is the permeability. of free space. It is a constant of the universe. So it's a constant you get when you do magnetism. The permeability of free space. That's the special constant. It's called mu naught. Again, mu is pronounced mu. It's the Greek little m. All right. So again, we've seen this. We've seen mu before when we talk about friction. And this is the same. This is called mu naught. All right. So it's like the kitty cat would say mu. All right. Mu. All right. So essentially, this is difficult. This is a difficult calculation. So essentially, the law of Biot-Savart can be most easily performed, as I've said many times, with other things, and in cases of high symmetry. So the law of Biot-Savart is most easily performed. So again, the law of Biot-Savart is very difficult to calculate in general. It is most easily calculated in situations of high symmetry, like a long, straight, current-carrying wire. All right, so let's pick a spot. Let's pick something that has high symmetry. So instead of that generalized wire that I drew, let's draw one that is long and straight. In fact, it's so long we can consider this infinitely long. All right, so long, straight, current-carrying wire. And so if we apply the law of Biot-Savart to that situation, let's kind of look at it here. Okay, so again, so long, straight, current-carrying wire. All right, so long, straight wire, so long as to be infinite. All right, so we would consider it to be infinitely long. All right, infinitely long wire. So long that I don't really care. If I have some point out here, point P, for instance, I have a magnetic field, I don't even care where I am with respect to the wire because, again, it's infinitely long, so how would I know if I'm closer to the top or closer to the bottom of the wire? So again, I can use symmetry. The wire has a current I, and again, I can consider a differential element IDS, just like last time. And if I add up all the current elements from negative infinity to infinity, I end up finding out that I can actually understand what the magnetic field is. B of R is mu naught I over 2 pi R. If I imagine that the length here, this distance here to the point of interest is R. So B of R would be right out here. B as a function of R, distance from it. Mu naught I over 2 pi R, again, for a long, straight wire carrying current I. Not for anything else, only for a long, straight wire is this true. And this goes on and on and on. Now I'm going to make a statement here about a second form of the right-hand rule. All right, so we're going to talk about the right-hand rule so far. There's actually a second form of the right-hand rule. All right, so let's kind of imagine this long straight wire. It's a good example of this. So there's a second form of the right-hand rule. Applied, or say applicable to the current form. I say current means I. The current form of the Lorentz force law. By the way, we talk a moment about Lorentz. You might wonder who that is. So Lorentz was a great Dutch physicist. All right. His name is Henri Antoine Lorentz. He was Dutch. He lived in the late 1800s and the early 1900s. I believe he got the 1902 Nobel Prize. I think his third Nobel Prize ever handed out in physics. Lorentz, and I'll talk more about Lorentz when we talk about atomic physics and quantum physics, but he did a lot of work in electromagnetic theory. Relativity. We'll talk about relativity in chapter 28, and quantum mechanics. We'll talk about quantum mechanics in chapter 29. Brilliant physicist, personal friend of Albert Einstein. So very important. He was much older than Albert Einstein. I don't think Lorentz really lived much into the 20th century. Most of his life was lived in the 1800s, but he did pass in the 20th century. He made a lot of great contributions. All right, so again, we talked with Lorentz force law. That's really named after him. All right, so Lorentz force laws. We have a second form of the right-hand rule. So we can think of it always as for F equals IL cross B. Either IL or B is the straight part, and I'll explain this in a moment. Of the calculation. Then the other is the curly part. All right, and so in this particular case, the straight part is the current. So for instance, the right-hand rule says the straight part of my hand, and the right-hand rule is my thumb, right? My thumb is the straight part. My fingers do the curling. So I use my thumb to indicate the straight part of the calculation. I use my fingers, how they curl around, to demonstrate the curly part. So in this particular case, my thumb goes along the current. So again, the current's going up in the page. My thumb goes along the current. My fingers curl around the wire. So the current in this case is a straight part. IL is a straight part. Then B is the curly part. So B is going to, if I put my thumb along the wire, B is going to curl according to my right hand, the right hand rule. So it's going to curl inward on the right hand side of this wire. If you look at the plane, around and out on the left hand side. All right. So again, my thumb is the straight part, and my fingers, I put my thumb in accordance, where the current goes. My fingers curl like the magnetic field will go. Magnetic field lines will go in concentric circles around this wire. And it does it in accordance with the right-hand rule. So on the other side of this, we'll see current actually coming, a magnetic field coming out. So again, it comes in and out. It goes in according to how my fingers would curl around the wire. Okay, and so the magnetic field forms concentric circles about the long straight wire. So I know that B of R, so first of all, I know the magnetic field forms concentric circles about the long straight wire. So for a concentric circle, for a magnetic field, with concentric circle of radius r, its magnitude is, or its magnitude is given by B of R, again, is mu naught I over 2 pi r. See, I know the direction and I know the magnitude. Now, again, this is all from the law of Biot and Savart. But again, Biot and Savart, law of Biot and Savart is a limited application. It's only good for a single wire. As I said earlier, I want to do better than that. I want to actually consider a distribution of wires. I want to have a current distribution. I want to be more generalized than this. So this is kind of like the magnetism equivalent of the point charge. This is a single long straight wire. All right, but I want to do better than that. So this takes me now finally to the second of the 4 Maxwell equations. And that Maxwell equation is called Ampere's law. So Ampere's law is a fundamental law of the universe. So it was named after, I've said this person's name before, André Marie Ampere. You know, excellent French physicist, André Marie Ampere. And of course, we Americans call it ampere. And so our unit of current is the ampere, and we even abbreviate it down to just say amps. So many milliamp current, or so many amps, right? So again, it's the person's name is Ampere. Now, Ampere's law. Now, again, it's a law. It's a statement, a law of the universe. There's nothing to derive. I just, again, Ampere figured this out. So what I'm going to do is I'm going to draw a little picture, and I'm going to show you kind of how to employ Ampere's law. So let's imagine we have a current distribution. So I have a current here, I1. So it's a wire coming out of the board right there. And I have another current, I2. And I have another current, now it's going into the board. And I have another current, I3. All right, and I'm going to draw a loop around this system, but I only want to care about I1 and I2. I want to exclude I3 for whatever reason. So I just really want to care about I1 and I2. So I'm going to draw what's called an Amperian loop. Okay, this is called an Amperian loop. So what I want to consider here is basically walking this loop in little tiny differential displacement vectors. So let's kind of pick one here, very small displacement vector. And I'll call it ds sub I. I'm going to walk the entire loop. All I basically means a number, it's an index. You've seen this before. So again, so it's a little displacement vector, and it's tangent to the Amperian loop. Trying to draw it here. Little displacement vector doesn't look too little. ds sub I. Again, I'll have ds1, ds2, ds3, ds4, all the way around. So again, I'm going to have other examples of displacement vectors. Maybe this is ds1. Maybe over here it's ds2 or whatever. I mean, again, they're all over the place, all the way around the loop. All right, and for each one of these displacement vectors, again, this is not very well drawn the scale, but these are differential. They're very, 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 very short. All right, and every single place along there is going to be a magnetic field. So it'll be a magnetic field. Now that'll be emanated at this location. We'll call it B sub I. Again, I'm looking at I. So this would be, say, B sub 1. Maybe this is B sub 2. So there's a magnetic field being given off by this current distribution somehow, some way, and I care about, in this particular case, there's an angle theta between ds sub I and B sub I. All right, so ds sub I is the ith. And ith means first, second, third, fourth, fifth, sixth, ith. I plus 1, I plus 2, so on and so forth. Again, it is a generalized way of counting. It's the ith differential displacement vector tangent to the Amperian loop about the current distribution. Okay, so again, and then B sub I is the magnetic field from the current distribution. At S sub I or at ds sub I. So the idea is I can consider these displacement vectors going all the way around the loop. I'm going to follow the entire loop, and I'm going to do the following calculation. This is what Ampere's law basically says. And these are a little different, little displacement vectors. I'm going to go around the Amperian loop, and this is what Ampere's law says. It says, add up all B sub I dot ds sub I, all around the Amperian loop. These are all dot products. That is equal to mu naught times the enclosed current. This is a law of the universe. Remember, these ds sub i's are all tangent to the Amperian loop. I draw the Amperian loop and I add up all of these dot products, b sub I, the magnetic field there, dot ds sub I. Again, I is nothing but a counting index, 1, 2, 3, 4, so on and so forth. You know, it's just a general way of saying counting index. So I add up all of these dot products all around the Amperian loop. And that's miraculously equal to mu naught, the permeability of free space, times the enclosed current. Let's write this mathematically. This basically says that the sum over all these all these indices, you know, these every single one of these displacement vectors all around the Amperian loop. I add them all up, and I add up all these dot products, b sub I dot ds sub I. Miraculously, that's mu naught I enclosed. That's the current enclosed by the Amperian loop. All right, enclosed by the Amperian loop. What is that? Well, one more line of algebra. Here's summation. In this particular case, summation over I. B sub I dot ds sub I is equal to mu naught. What is I enclosed? Well, in this case, it's just I1 and 2. I'm ignoring I3. I want to exclude I3 for whatever reason. Well, I1's coming out of the board, so I guess I'll call that positive. It's positive z hat. So I1 minus, and I2 is going into the board, so it's difference. I1 minus I2. That's all the right-hand side is. So by a miracle, this is Ampere's law. Now, of course, we want to consider differential displacement vectors. And so what we really want to do is add the calculus style. So you would see in a university physics book or some more advanced physics book, you would see Ampere's law written like this, adding up the calculus style. That's called a line integral. You need to have calculus 3 to really do that kind of integral. Line integral is a fancy way of saying we're adding up these differential lines, displacement vectors, and it will be written as b dot ds equals mu naught I enclosed. So that would be the formal version of Ampere's law. Here is the college physics version of Ampere's law. All right, and really it's just a matter of adding up. It's you know, there's no reason for this to be true. It just is. It is a law of the universe. All right, by a miracle, if I add up all these dot products of magnetic field with these displacement vectors all the way around the Amperian loop, it's equal to mu naught times the current that's enclosed in this loop. And well, I get what I want, right? I mean, I essentially have what? When I do this calculation, if I can do this calculation, I will get B as a function of I. I will know, basically I'll answer the question. For some current distribution, what is the magnetic field located at some place? I draw my my Amperian loop such that I can figure that out. My Amperian loop would go through the point that I'm interested in, evidently, right? And so that is what that's the name of the game. This answers the fundamental question given a current distribution, what's the magnetic field at some location in space? Now, of course, as I've said many times, you know, the applying Ampere's law is generally difficult to do. You want to apply it in again situations of high symmetry. Well, let's do it for the long straight wire. All right, so let's consider. So again, employing Ampere's law is generally hard. So let's do it for high symmetry. So again, applying Ampere's law is generally difficult. And most easily done in situations of high symmetry, like long straight wire, like the long straight current carrying wire. All right, so let's do that. Let's apply Ampere's law and see if we get the same answer that Biot and Savart would get. All right, so let's apply Ampere's law to the long straight wire. See how we can do that. All right, so again, long straight wire. Long straight wire carrying current I, and again, empirically, we know that if I put my thumb up along the direction of the wire, the magnetic field is going to make concentric circles. So let's say somewhere over here, the magnetic field is going into the board at a distance r, and on the other side is coming out of the board a distance r. So again, the magnetic field forms concentric circles. Now, well, what do I want to do? Well, again, I have the simplest situation here. I have a long straight wire, a single wire, in fact. So let me draw my Amperian loop. Nice circular Amperian loop. Make it as simple as possible. So I'll make a nice circular Amperian loop that goes right through where I want to go. And again, this doesn't look much like a circle, but let's kind of pretend I drew a circle here. It's going to look oval anyway, in the manner in which I draw it. But so I'm going to draw a circular Amperian loop about the wire. So draw a circular Amperian loop about the single long straight wire carrying current I. The Amperian loop has a radius r. Okay. So we're going to go about this Amperian loop, and we're going to employ Ampere's law. All right. So interestingly enough, here now you might ask yourself the question, well, hey, wait. So you're applying a nice circle this time. Why didn't you do a circle in your original example? Well, the reason being is I can't draw a circle there because I'm trying to avoid I3. There's no way that I can draw a circle that would include I1 and I2 at the distance I'm considering without also including I3. So I had to draw a more complicated Amperian loop in order to avoid the inclusion of I3. Here, I don't have such a restriction. I have a single straight line, straight current, one current. I can make it a circle. So so before, in my example, I could not draw a circular Amperian loop. Because I could not draw a circle that would include I1 and I2, but exclude I3. Again, for whatever reason, I want to exclude I3 in that example. Here, I only have one single current, so I can just draw a circle. All right, so again, nice and easy. Now, a couple other nice things about this situation. First of all, the differential displacement vectors are going to be, they're always tangent to the Amperian loop. So again, differential displacement vectors the S sub I are always tangent to an Amperian loop. And here, they are tangent to a circular Amperian loop. Even better. Okay, another very important point. The magnetic field forms concentric circles. About the Amperian loop, or sorry, about the about the strong straight wire, about the long straight wire, where that came from. So at any point on the Amperian loop, on the circular Amperian loop, in this special case, B sub I and ds sub I are aligned. So a lot of good stuff happening in this high symmetry situation. They are always aligned. All right. Well, that helps my calculation out quite a bit. All right, so kind of considering everything I've said here, let's now write down Ampere's law. Ampere's law is, again, the summation over all these current elements, or of all these displacement vectors, all the way around. We have the dot product of B sub I dot with ds sub I. That's equal to mu naught I enclosed. That's the current enclosed by the Amperian loop. Okay, what I just say is that, first of all, B sub I and ds sub I are aligned everywhere. Along the circular Amperian loop. So the dot product then becomes like this. B sub I dot ds sub I. These two vectors will then be the magnitude B sub I times the magnitude ds sub I times the cosine of 0 between them. Cosine of 0 is 1. So nicely, I can change the dot product multiplication with an ordinary multiplication. So in this particular case, I can now say that B sub I dot ds sub I, in this special case, is nothing more than just the magnitude B sub I times the magnitude ds sub I. So I can change that dot product calculation for an ordinary calculation, an ordinary multiplication. So I go up here, I can take off the hats. Well, here, well, I can take off the hats, and it's no longer a dot product. So this becomes an ordinary ds sub I multiplication. All right, so again, it's just ordinary multiplication of scalars because of the situation. I enclose. Well, the only I enclosed are just I. There's only one current in here, so this simplifies to simply I. All right. Now, by symmetry, and by experiment, this has been checked out. The magnitude of the magnetic field is constant. About a circular Amperian loop, or about a circle, or in constant anywhere on a circle, on a concentric circle, about a long straight wire. All right. And again, it makes no sense for me to believe that the magnetic field anywhere on the circle would be any different than it is anywhere else. So what that means is that if it's constant, if B is constant, then that means I can take the I off of the B in the calculation. It's constant. The magnitude of the magnetic field is constant everywhere about the circle. So if B is constant, I can just say that, well, the summation over I of B times ds sub I is mu naught I, since B is constant. On a circle. And not constant everywhere, just constant along a circle. All right. So what that means is I have a constant. Here's the summation. I have a constant multiplied by something that actually is summed over. So as I've said many times in class, you can actually extract the constant out in front of the summation. I can extract it. So because it's a constant, it doesn't take part in the summation. So I can actually write it as B times the sum over ds sub I is mu naught I. Now, what's the sum doing now? Well, what I'm asking now is that I want to add up all these little segments all the way around the circle. Isn't that the same as the circumference? It is. So I can actually instead write this as B times the circumference. I'm just adding up all the way around the circle, right? It's mu naught I. And what's the circumference of a circle? It's 2 pi r. So B times 2 pi r, again, a circle of radius r, is mu naught I. And finally, I have derived the result that Beal and Savart got, that the magnetic field as a function of r is mu naught I over 2 pi r. Again, this is only true for a long, straight wire. This is kind of like when I applied Gauss's law to a conducting sphere. Remember, I was able to retrieve Coulomb's law from that. Well, here I've applied Ampere's law to one single long straight wire, and I'm able to obtain the same equation as you would get if you employed the law of Biot and Savart about a single long straight wire. So again, it's a very similar kind of a correspondence. So again, what I've shown you is that you can use Ampere's law, which is the second of the Maxwell equations, and you can use that in general to express the magnetic field as a function of the current distribution. All right. Now, again, many times applying Gauss's law is a difficult. Applying Ampere's law is a difficult task. So you try to apply Ampere's law in various situations. So let's try to look at a couple other different situations now. Let's look at a situation of current going in a wire loop. All right. So again, we're not going to calculate this, but let's kind of look at another situation. That was a current in a long straight. That was a magnetic field about a long straight wire. How about a magnetic field produced? And I'm just going to give you a result. Magnetic field produced by a current carrying circular loop. So again, another situation. Now you don't have a long straight wire. Now you have a situation where you have, let's say, a wire and it's bent in the shape of a circle. Comes back around. So current comes in, it goes around the wire, and it comes back out. And again, we'll say this circle is radius r. Now, again, we can sit there and divide up the current in little tiny differential segments like we did last time, and employ a more complicated version of Ampere's law. And what we would find is the magnetic field lines are complicated. The magnetic field lines would go through this wire loop, and I'll try to draw it the best I can. You'd have a kind of field line going around like that, and again, you imagine they're going through the wire loop. And this is the magnetic field, and you have something coming through here like this, and maybe like this, and so on and so forth. You'd have a complicated arrangement of these magnetic fields. So it'd be complicated, and it'd be hard to calculate. But one of the things that we do know, though, is we have a hard time calculating the magnetic field, through this arrangement. You see the magnetic field lines would be complicated, but we do know what the magnetic field is through the very center of the loop. All right, so the magnetic field strength through the center, just the center of the current carrying loop looks kind of similar, except so it's going to be B at the center is mu naught I over 2R, no pi. So that would be through the center, only the center, only one magnetic field that we understand. We know what the magnetic field is through the center of this arrangement. Nowhere else do you have a simple formula like that. Again, that's just another example. If they ask you, you have a current loop and one magnetic field at the center, through the center of this current loop, well, you can say, oh yeah, I know that equation, mu naught I over 2R, no pi. Okay, now, next application where I'd like to discuss Ampere's law is actually very important. Now, we have said back in electrostatics, we constantly kept coming to the parallel plate arrangement. The parallel plate arrangement. We kept on saying that. We go back to our favorite arrangement, the parallel charged conducting plates. And we eventually made a special current element out of it. We made a parallel plate capacitor. So it was so important to us, we actually made a special current element out of it. Well, we're going to derive right now the very special go-to object that eventually is going to become a current element. It's going to become what we call the inductor. But we have a special go-to object. It's called the coil. We have a special fancy name for it called a solenoid. So a solenoid is a long coil of wire. Okay, with many turns or loops. As opposed to a flat loop, like we had before with the motor. All right, so what I might do is, let's try to do my best here to draw this picture. So I have again, the solenoid is hollow. And so let's imagine that I would have, let's say, a wire, and it comes off say from a battery. So I have a battery down here. We'll say this is a plus terminal and the minus terminal. And so the solenoid is going to come up, it's going to bring current. And what's going to do, we're going to essentially have very tight coils. Going to wrap around many, many turns. This is many, many turns of wire wrapping around the solenoid. Each turn of wire, then eventually you'll get to the point where you're at the end, then you come back and you connect back to the battery, so you have a current going through. All right, and so again, there's going to be a current I in each one of these turns. All the way around, each one of these turns. And so what's going to happen is, what's nice is that when you have, so remember, each loop is going to have a magnetic field. So you have a curly part and a straight part. This time the curly part is I, and the straight part is B. Okay, one of them takes the turn of being curly, the other one takes the turn of being straight in the Lorentz force law. So each one of these are going to contribute a B. So each one of these coils, each one of these loops of wire is going to contribute to the magnetic field. And so you're going to get a very strong magnetic field coming out parallel to this axis. Strong, uniform magnetic field. So just like I said, with in the case of parallel plates, I asked, well, how do we make a nice uniform electric field? Well, we have two parallel conducting plates. And again, we liked it so much, we made a capacitor out of it. We made a parallel plate capacitor. Well, here's a situation where I want to have an arrangement where I can actually create a nice, strong, uniform magnetic field. And I do it via a coil. So this is basically a tight coil. Tight coil of wire, many turns. All right. So what I have to actually do, now we call this a solenoid. Solenoid is very important. You have at least one solenoid in your car. Very important. It's that we actually will use the solenoid. We use a coil to eventually make an inductor. So in fact, back when I said, remember our circuit elements, we have the capacitor. Okay, it looks like parallel plates, right? We have the resistor. Here's the capacitor, here's a resistor. Well, it turns out that the circuit element for a conductor is none other than a coil. And we use L for inductance, well, for whatever reason. But again, the inductor, which is the third circuit element we'll study in the next chapter, actually, we represent it on a circuit diagram as a coil. So again, a lot of parallels here, right? Now, remember back in our study of capacitors, we actually used Gauss's law to figure out a relationship between electric field and charge. Well, we want to find a magnetic field with respect to the current. We are going to use what? We're going to use a Maxwell equation. In this case, it's going to be Ampere's law to figure out the magnetic field in a solenoid. So again, a lot of parallels here. All right. So I want to use Gauss's law. I'm sorry, not Gauss's law. I'm sorry, Ampere's law. So I'm going to look at a cutaway of the solenoid. So I want to give myself some space. I'm going to erase this picture, and I want to actually look at a cutaway picture of the solenoid. So I want to imagine the solenoid. I'm not actually going to cut it in half, but I'm going to pretend that I can actually see half the solenoid. So let's take a look at a cutaway diagram. That's what they call it in engineering, a cutaway diagram. Of a solenoid. All right. So if I took a look at this, I imagine cutting it in half. Well, I have, you know, a wire here. So current, I'm going to kind of blow this up a little bit. So current is doing what? It's coming in, going around in a circle, and it's coming out the other side. And my cutaway, the next one, I have current coming in, going around the circle, coming out the other side. Again, in, coming out the other side. And my drawing is, you get the point. I mean, it's basically a cutaway of the solenoid. I'll draw one or two more. And the idea is this is the cutaway of the solenoid. This is essentially like cutting the solenoid in half. So current comes in on the top, and each one of these is carrying a current I. Each one of them. This carries a current I. All of them carry a current I. Okay? Now, what's going to end up happening is you'll see very strong magnetic field coming out through the solenoid. So you'll see all these magnetic field lines, nice and parallel, going along the axis of the solenoid. All right, and caused by what? The right-hand rule. Now the question is, I would like to, let me draw analysis purposes. All right, so I would like to consider a certain section of the solenoid and employ Ampere's law. So I'm going to draw an Amperian loop. Say right here, a little rectangle. I'm going to draw a rectangular Amperian loop. And I'm going to label it A, B, C, D. I'll call this A, B, C, D. My Amperian loop, okay? This is an Amperian loop. Basically about a section of wires that are coming in. I probably should do a better job at least include this entire wire. I'll call this A. Let's see it better. There's A. A, B, C, D. All right, A, B, C, D. Now, this is an Amperian loop. All right, now, what I want to do is I'm literally drawing the Amperian loop, and there are wires going through this loop. There's current from this section of wires I'm so choosing that are going through this Amperian loop. That's going to be my I enclosed in my Ampere's law. Now let's do something else. Again, this is my Amperian loop, as I said before. Let's imagine this loop has a length h. Right here, from C to D is h. All right. Let me employ Ampere's law. So Ampere's law is going to say the sum of all B dot, I'm going to say, instead of D, I'm going to say B dot S. So I'm going to say the sum of all B sub I dot S sub I is mu naught I enclosed. And I'm employing Ampere's law about this Amperian loop, about this cutaway section of this solenoid. Again, these are all wires, many turns of wires, current going in, current coming out, current going in, current coming out, so on and so forth. And I really want to figure out the current that's coming into this Amperian loop. I'm going to draw the Amperian loop about that. It's a rectangular Amperian loop. Okay, so what is this really telling me? Well, I want to do B sub I. I'm going to do basically B dot S going from my I is really going to be A to B, B to C, C to D, D back to A, right? So I have B dot S going from A to B plus B dot S AB going from B to C. Just walking, I'm walking the loop. Plus B dot S going from C to D plus B dot S going from D back to A. And that's going to equal the right-hand side. Again, I'm not going to touch it yet. Mu naught I enclosed. All right. Now, turns out that this is actually going to be a really easy problem. First of all, let's look at BC and DA. BC and DA, remember, empirically, I can determine that the magnetic field is absolutely going straight along the axis, which means it's perpendicular to BC and DA. So that means that B, which is one single magnetic field, B is perpendicular to legs BC and DA. What's that mean? Well, that means that B dot S along those legs is the magnitude of B times the magnitude of the displacement X times the cosine of 90 degrees. They're perpendicular. The cosine of 90 is 0. That means that the contribution along the legs BC and DA are 0 because they are perpendicular. So automatically I can eliminate those. BC because it's perpendicular, DA because it's perpendicular. Those are two terms that are automatically gone because they are perpendicular. The actual displacement leg is the displacement leg along the Amperian, rectangular Amperian loop is perpendicular to the magnetic field. All right, I have another simplification. How about CD? Well, along leg CD, here's the beauty about the solenoid. The magnetic field just outside a solenoid is 0. I don't care how close you get to the solenoid, the magnetic field just outside the solenoid. It's very strong inside the solenoid, but outside the solenoid is 0. So magnetic field outside the solenoid is 0. So B equals 0 along displacement leg CD. So again, because there's no magnetic field outside the solenoid, this term goes away. Those three are gone. The only term that's left is AB, and it turns out that AB is pretty easy to do as well. Basically, along AB, the magnetic field and the displacement are parallel. All right, and so the displacement S, so B and S so B and S along leg AB are parallel. So B dot S is nothing more than just B, magnitude of B, times the magnitude of S. What is the magnitude of S? It's H. That's the magnitude of S, the total magnitude of that leg. I already said it's H. So it's BH, and then times the cosine of 0, and the cosine of 0, that's 1. So literally, This is nothing more than BH. So all this calculation with this rectangular loop, this rectangular Amperian loop, the entire left side has just reduced to nothing more than BH. All right, so let's kind of simplify that and write that. So what I now have is, with all of this said, I really have is that basically Ampere's law has now reduced for this situation as the left-hand side has just reduced to BH. And that's mu naught I enclosed. All right. Now let's now work on the right-hand side of this equation. All right. So what's I enclosed? Well, if you pick up a solenoid off the shelf or any kind of inductor off the shelf, you know, an inductor, coil, or solenoid is rated by the number of turns of wire per length. We usually call this little n. So you pick up a solenoid or a coil and you just read off what little n is. The manufacturer usually tells you what that number is. What's that number? What is little n here? Well, you can think of it like this. You can say, well, little n, let's just say if I were to count all the loops here, 1, 2, 3, 4, 5, 6, 7, whatever, all the loops that are all the wires, all the turns of wire that are in this length h along the solenoid. Well, let's just say there's capital N of those counts, and I just count them, 1, 2, 3, 4, whatever, how many all the way along the length h. And again, it's that many loops per h. So if I know that there are n of these loops, each loop contains a current I. What's the I enclosed? Well, it would be what? It would be BH is then going to be mu naught. What's I enclosed? Well, I have basically n of these turns, and each one contains a current I. Every one of them. I, all the way through. N of these turns, every one of them. This is the number of turns. So n, again, is number of turns of wire in length h. Okay, so each turn is going to carry a current I. Wait a second though, I can solve this equation and say, well, fine, I'm not given a number of turns usually. I'm usually given the turn density, number of turns per unit length. So let's just solve that. Well, okay, fine. Instead of n, I can just write little nh, cross multiply. So I'll stick that in here. I'll substitute that in here. And then I get that basically BH is mu naught NHI. H is canceled. And so I now have an expression for the magnetic field for the solenoid. And it is the following. B is mu naught Ni. That's a magnetic field for a solenoid. Again, there's a solenoid of carrying current I with N. So little n is the number of turns per unit length. Mu naught, again, is the magnetic permeability of free space. That's the relationship. Again, what am I after with Ampere's law? I want a relationship that says what is the magnetic field for a given current distribution. This is my current distribution for Ampere's law, from Ampere's law, and then this is the magnetic field. That is what I'm after. I'm after a magnetic field as a function of the current. So Ampere's law gives me that. Now again, this relationship, this equation is only good for a solenoid, a coil. Now we're going to see that the coil, particularly when we go to chapter 22, that the coil is a go-to item for electromagnetism, particularly dealing with magnetism, dealing with, you know, in our development was called the inductor. Okay, we have one last topic of chapter 21. And so this is something, this topic here is something that is easily seen in the laboratory, extremely easily seen in the laboratory. And so, and it is magnetic forces. A magnetic force between parallel current carrying conductors. So if I go to the laboratory and I set up a situation, let's say, oh, you know, I'm gonna set up a situation where, well, I have a wire, nice long straight wire, and it's going to carry a current I1, and I have another wire parallel to it, long straight wire, again carrying a current I2. I turn on those, and let's just say, for instance, that there's a distance d between them. I turn on these currents, and I'm going to find out, interestingly enough, that they attract. They'll attract together. And if I were to actually set up, you know, in a different situation, let's say one current going one way and the other one going anti-parallel, and I turn them on, they repel each other. I'm going to find out that parallel currents in the laboratory, I find out that parallel currents attract and anti-parallel currents repel. Interesting. Can I, with the knowledge of physics that I have right now, can I actually explain how that works? And the answer is yes, I can. So let's see how this works. Let's imagine that I like to understand, I'm going to focus on current 2, and I like to understand how current 2 will be affected by the fact that there's a current, how the current, how wire number 2 that carries current 2 is affected by wire number 1 that carries current 1. How is that happening? Well, I know that wire 1 has a magnetic field. So let me, I need some real estate here. So I know that wire 1 has a magnetic field, all right? So it has a magnetic field, B1 of R equals mu naught I1 over 2 pi R. Again, this is from wire 1. Right? It has a magnetic field. Well, what's a magnetic field look like? Well, again, if I put my thumb up along that wire, it's going to curl around the wire. So it's going to come around, and by the time it gets to, let's say, D away, wire 2 sees it as coming into the board. So it's coming in all the way around, and it's coming back out on the other side. But as far as wire 2 is concerned, it's a magnetic field into the board, right? And so wire 2, so again, the B1 of R is concentric about wire 1. Wire 2 is coplanar. I mean, it's in the same plane here, same whiteboard. It's coplanar to wire 1. Wire 2 sees B1 as into the board, where it is. Again, why is that? Again, if I put my thumb along wire 1, the magnetic field goes along in concentric circles. So if it's concentric circles, well, by the time it gets coplanar, it's seeing it as down. It's seeing it as going into the board. And so we see over here, we see B1 as effectively down into the board. That's what wire 1 sees. And again, it's at D away. So what it sees here is that B1 at D will be mu naught I 1 over 2 pi D into the board. All right. Okay, well now, so effectively wire 2 is seeing a force, a magnetic field that's straight into the board. But wire 2 has a current that's going up. So wire 2 is going to feel a magnetic force. So the force basically on wire 2 due to wire 1, we'll write it like this. The force on wire 2 due to wire 1. All right. The force on wire 2 due to wire 1 is going to be what? It's going to be I. So again, IL cross B, right? What I? Well, I2. We're talking now about, we're talking from the perspective of wire 2. The force on wire 2. So again, this is the force on wire 2 due to wire 1. Wire 1 has a magnetic field, and so it effectively is giving a downward, because of the way its concentric circles are. By the time it goes to a coplanar location, that magnetic field is straight down to the board. And so it's feeling an IL cross B. What I? Well, we're talking about wire 2, right? So it's going to be I2. We'll consider some section of L, some section L of the wire, cross B. What B? B1. So it's going to be I2L cross B1. It is the current in wire 2 multiplied by a length vector crossed with the magnetic field it feels from wire 1. All right, and so what direction would that be? Well, again, right-hand rule. I2 going along the wire, cross B. It feels an attractive force. It feels a force toward wire 1. So it is going to feel a force, magnetic force, toward wire 1. So basically, it's going to feel it's going to feel a force F21 will be I2 L B1 to the left. Or we know what B1 is, right? So F21, well, I2L, what is B1? It's mu naught I1 over 2 pi D. That's what B1 is. That is the B from Ampere's law with respect to wire 1. So again, it's I2L, and B1 is essentially felt, it's the magnetic field from wire 1, and I know how to calculate that. That's mu naught I over 2 pi r, or mu naught I1 over 2 pi d. So I can clean this up and say that the force, I can just write it up here in a parking lot, the force on wire 2 due to wire 1 is going to equal mu naught L I1 I2 over 2 pi d. And where's it going to go? It's going to go toward the left. It's going to go left toward wire 1. All right, well, great. Let's switch perspective. Let's now consider, well, let's look at the perspective of wire 1 and how it gets affected by wire 2. Okay, so now let's look at wire 1. I want to look at F12 per se. So again, I'm looking at wire 2 creates a magnetic field about it. How is its magnetic field going to be? Again, I'm looking at B2. Again, I want to figure out how does wire 1 get affected by wire 2. I'm going to switch roles. So now I'm going to look at wire 2. So okay, well, I'm going to put my thumb along wire 2. The wire 2 again is going to have concentric circles of magnetic field. So it's going to be, so for wire 2, it's going to be into the board over here, but it's going to be out of the board on the other side. Again, it's concentric circles. Well, it's going to be out of the board when you get to wire, so again, this is B. When you get to wire 1, wire 2's magnetic field, B2, is going to be out of the board at a coplanar wire 1. So again, B2, by the time you get to wire 1 that's D away, it's going to have an effect of being out of the board. That's your B2. Its effect, we got to find out what is its effect on wire 1. All right. So again, we know what B2 is. B2 of R by Ampere's law. Mu naught I what? I2, right? Because we're talking about B2. Mu naught I2 over 2 pi R, or of course at a distance D. Again, wire 1 is D away from wire 2. B2 at D away is mu naught I2 over 2 pi D. Fantastic. And it is out of the board. Now the question is, well, what effect is that going to have? What direction is it going to go? So again, I got to look at Lorentz force law again. So again, I'm looking at what? I'm looking at the force on wire 1 now due to wire 2. Again, F12 means, in my nomenclature, it's the force on wire 1 due to the effects of wire 2. Again, I'm switching roles from last time. So again, if I'm looking at IL cross B, what I am I talking about? Well, I'm talking about I1. I1L cross what B? Well, the B from B2, the B from wire 2. So I1L cross B2. Again, I'm focusing on wire 1. I know that wire 1 is a certain current and it's being affected by a magnetic field. A magnetic field that's basically concentric about wire 2. And oh, by the way, when it's D away on a coplanar wire that's parallel, it's going to look like it's coming out of the board at wire 1. So what direction is Lorentz force law going to tell me? Well, let's see. Let me again line my fingers up along the wire. And what am I saying? I'm saying the wire is going out of the board, right? At this point, the magnetic field is going out of the board. So IL cross B, my thumb points inward. My magnetic force, F12, will be to the right, will be toward wire 2, right? And so I'm saying I know that F21 was a force toward wire 1, and F12 is a force toward wire 2. So they attract each other. They're attractive. And so what I can do is I can put all this together. I say, well, F12 is I1 L B2 to the right. All right. And so let's consolidate here. So with all this said, F12 will be I1 L, and I know B2. I know B2, right? It's by Ampere's law, it's mu naught I, oops, hang on, this is I1. So again, F12 is I1 L, and what's B2? It is mu naught I2 over 2 pi d. So again, plugging it all together, I have something interesting here. I have F12 is mu naught L I1 I2 over 2 pi d, same magnitude, but now it's right toward wire 2. The forces, the attractive forces between these two, they're F12, basically F12 causes wire 1 to be attracted to wire 2, and F21 causes wire 2 to be attracted to wire 1. And their magnitudes of attraction are the exact same formula. Mu naught L, I1, I2 over 2 pi d, mu naught L, I1, I2 over 2 pi d. If I were to do this exact same calculation, except have anti-parallel currents, I would actually find out that they repel. I would go through the exact same formulation, find these exact same answers, same magnitudes, and I would find that they would just, when I applied Lorentz force law, I would find out that the wires would be repelled from each other. All right, so it's very, very interesting. So again, this is F21 means the force on wire 2 due to the effect of wire 1. F12 is the force on wire 1 due to wire 2. They're mutually attractive to one another. And this is their magnitude of the force. Mu naught, the permeability of free space, times L, the length of the wire considered, times I1 times I2, the product of the currents, divided by 2 pi d is the distance between these two parallel wires. So if I do it all together, I will find out, and I will also agree with what I would find out in the laboratory. And that is parallel currents attract and anti-parallel currents repel. And we know how to do it, and I just derived it. So again, parallel currents attract. Anti-parallel currents repel. And I went through the derivation to show you how two parallel currents attractive. Again, it'd be the same deja vu type derivation if I were to show you how two anti-parallel currents repel. All right, all I have left to do for the rest of this lecture is basically 3 quick problems. All right, so let's do some parallel wire problems here. So let's look at OpenStax 22.50. Okay, A, the hot and neutral wires supplying DC power to a light rail commuter train. Carries 800 amperes. And are separated by 75.0 centimeters. What is the magnitude and direction? I guess I should say what are magnitude and direction? Of the force between 50.0 meters of these wires. B, discuss the practical consequences of this force, if any. All right, so here we go. 22.50 open stack says, A, the hot and neutral wire supplying DC power to a light rail commuter train carries 800 amperes, okay, two wires, 800 amperes each, and are separated by 75.0 centimeters. What are the magnitude and direction of the force between 50 meters of these wires? All right, so again, 50 meters is my L in my equation, 800 amperes, that's my I1 and my I2, they're both 800 amperes. And 75 centimeters is my D, okay? And then B is discuss any consequences of this force, if any, all right? So it's again, it's a parallel wire, or actually we'll find out it's actually anti-parallel, but hang on one second. All right, so hot and neutral wires. So the current, so again, we're talking about, now when you're talking about electrical safety, you know, you have the hot wire. Its current will say go this way. Now, if you put the neutral wire next to the hot wire parallel to it, what's it going to do? It's going to attract. You don't want wires attracting. If they attract, they will possibly short. You want to try to make sure you prevent any kind of shorting, which again is, as I've told you before, that causes, you know, I²R heating and possible fires and everything else, right? So the idea is typically your neutral wire you want to have set up so that it is anti-parallel, right? So this is your neutral. All right, so my I in each of these cases is a whopping 800 amperes. That's a lot of current. And D is their separation distance. Okay, D, I was told it was 75 centimeters, but again, I want to put it in meters. 0.750 meters, and their total length L, again, it's the length of the wire being considered. L is a long, very long 50 meters. All right, and so again, I can use either of the equations. I'll say F12, like we just got done deriving. What was that again? Mu naught L I1 I2 over 2 pi d. Again, you directly using the equation. I want to see what is the force between these two wires. All right, and so F12, I need space, mu naught is the permeability of free space. 4 pi times 10 to the negative 7 Tesla meter per ampere. That's the constant of the universe, the permeability of free space. The length of these wires is 50 meters. Okay, the current, so they're the same. I1 and I2 are just I, so I'll just call it I squared. So in this particular case, I could just say I squared because the two currents are the same, right? And so in that case, I is 800 amperes, so it's just 800 amperes squared. And I could do that because they're the same again. And then divided by 2 pi d, I have 2 pi, and again, d is 0.750 meters. Again, you want to go to SI. When you work all this out, you find out that the force between these two wires is equal to 8.53 newtons. And the wires repel one another since they are anti-parallel. They're anti-parallel by design, as I said. Just one less chance of being finding a short. All right, so 4.448 newtons in a pound. So we're talking about pretty close to 2 pounds of force there. You know, and if you think about it, kind of a, you know, I always, as much as I've been doing physics for 30 plus years, I still have to go to the American or English units to get an idea physically of, you know, how much is this? I mean, I have a much better understanding of pounds than I do newtons, unfortunately. I wish it was the other way around. I mean, I calculate newtons, but when I really want to kind of get an idea of what does that really feel like, then I end up going to English system, and that's true for any American physicist. All right, so part B, so that's part A. So part B talks about implications or practical consequences. So part B, may I say the force is repulsive. Therefore, there's never a risk that the two wires will touch and short circuit. There's not really too much to worry about. All right, that's all I wrote for B. All right, let's do another. We're gonna do one more parallel wire problem, and we'll do one solenoid problem. We'll call it a deal. So I'm going to look at OpenStax 22.52. That says a 2.50 meter segment of wire. Supplying current to a motor. Of a submerged submarine. carries 1,000 amperes. And feels a 4.00 Newton repulsive force from a parallel wire. .00 centimeters away. What is the direction and magnitude of the current in the other wire? So a lot of information in this statement. All right. So 2.50 meters segment of wire, that's L, supplying current to a motor of a submerged submarine carries 1,000 amperes, that's I, and feels, or I1, I guess, and feels a 4.00 Newton repulsive force, there's your F, from a parallel wire 5.00 centimeters away, there's your D. What is the direction of the current in the other wire? So again, what we don't know is I2. We know I1, we don't know I2, we also don't know the direction. We got to think about the direction, but actually you kind of do know the direction already, right? Because the way it says it feels a repulsive force, right? So the word repulsive means that the other wire's got to be anti-parallel. So I know that right off the bat, just from reading it. It's got to be anti-parallel because the two wires repel each other. Only anti-parallel wires repel. So I know that just by reading the question without even doing the calculation, right? So anyway, let's do the calculation real fast. All right, so again, we have a laundry list of variables. The segment length, I kind of read them off, but I read the question. The length of the wire segment in question is 2.50 meters. I1, I know that's given to me, it's 1,000 amperes, but I don't know is I2. Right, as I said, the force between the mutual force, the repulsive force, as it was said, between these two wires is 4.00 newtons. And let's see, what else do I know? The distance between D is going to be, I said it's 5 centimeters, but it's really, again, you want to put it in meters, 0.050 meters. All right. What's my equation for the mutual attraction or repulsion in this case? F12 is mu naught L I1 I2 over 2 pi D. I will then just solve for I2, simple algebra, put the 2 pi D on top, divide by the mu naught L I1. I get that I2 is simply going to be 2 pi D I1. Oh, I'm sorry. 2 pi D F12. And then divide by the rest of it. Mu naught Li1. And there you go. And it's a matter of now just plugging in values. So I2 is 2 pi. D is 0.050 meters. F12 is 4.00 newtons. Divided by mu naught Li1. Mu naught. Permeability of free space, 4 pi, times 10 to the negative 7 Tesla meter per ampere. All right. L, 2.50 meters. I1, 1,000 amperes. And again, I'm just plugging in the values that I know. I do all this calculation. I find out that I2 is 400 amperes. And again, I1 and I2 are anti-parallel. Since their interaction force, as we're told, and I just told you this right off the bat, just from reading the question, is repulsive. All right, so I know anti-parallel wires repel. All right, so this is my answer. All right, last problem. This was a solenoid problem. All right, so we did solenoids as well as the parallel and anti-parallel currents. All right, this one, I didn't find any good questions in OpenStax. This one's right out of your book. Cutnell and Johnson, I put a CJ. Pretty much every problem I've ever done here in these lectures so far has been OpenStax. So remember, CJ is Cutnell and Johnson. And again, we are actually in chapter 21 of Cutnell and Johnson. So it's going to be C, Cutnell and Johnson, 21.54. A long solenoid. Okay, has a length of 0.65 meters and contains 1,400 turns of wire. Okay, there is a current of 4.7 amperes. In the wire. What is the magnitude of the magnetic field within the solenoid? So this is a straight application problem. Magnetic field inside the solenoid. All right, so again, we are told the length of the solenoid, which we'd probably call H in our derivation. We're also told capital N, which is the 1,400 turns in that length of solenoid. And we're also told the current of 4.7 amperes. All right, so let's kind of keep that in mind. So let's, I need to erase for real estate purposes. All right, so it's a basic application of the solenoid magnetic field equation. We know what the magnetic field is of a solenoid, all right? And so again, the equation that I derived is that B is mu naught Ni. Well, we want to find B. The permeability of free space is always a constant universe. We're given capital N and H. We have to calculate little n. Remember, that's a linear density, and we're given I, right? And so we're given that the current actually in the wire that's wrapped around many times in the solenoid, we're given that current is 4.7 amperes, all right? Now, I'm given a total number of these turns. I'm told there's 1,400 turns in a length L. Or we'll say length H, and that H, that length H is 0.65 meters. We'll say L. So L is 0.65 meters. That's the length of the solenoid. So I need to form N, which is the ratio, nothing more than the ratio, but the number of turns per unit length. Well, I was told that I have 1,400 turns and a 0.65 meter length. And so we would figure out from that I'd have 2154 inverse meters, usually how you would, or 2154 turns per meter. It's usually how you would quote this. Well, I'm ready to plug it in. So B is mu naught 4 pi times 10 to the negative 7 Tesla meter per ampere. All right, N is 2154 inverse meters. I is 4.7 amperes. When I multiply those three numbers together, I find out that the magnetic field, nice constant uniform magnetic field that is going through my solenoid, will be 1.27 times 10 to the negative 2 Tesla, or I could write it as 12.7 millitesla. All right, so there's a basic problem for the magnetic field, nice uniform constant magnetic field that you would find inside of a solenoid. And that's all I have for this lecture.